All the details. Yeah. Okay. So this morning is marks the beginning of the last day of our symposium, and so leading us off this morning is Daniela Leo with her heat transfer coefficient analysis project.
Yes.
Go ahead.
Thank you, Mr. Broad. Good morning, everyone. My name is Daniela Leão, and I'm going to present an analysis on heat transfer coefficient. My advisor is Mr. McGregor, that's over there. So this is the agenda for my presentation. So I'll start with a brief introduction on heat transfer coefficient, thermal convection, and then I'll go over the functional overview of my project. That is basically the block diagram where I explain what I did. Then I go over the technical description. So I describe here the methodology, and I present some results, some discussions, some calculations as well. And then I'll go over the testing and results for my project. So I chose here 2 critical parameters for my project to occur. And then I'll conclude my project answering to a question that I proposed in the beginning of this project. And I'll show you the references I used as well. So the reason I chose this topic is because heat transfer coefficient is an essential tool to measure how efficiently a fluid or a cooling system can transfer heat. But it's not very easy to find this number in the literature. So in the literature, you find that for the air, for example, you find that the heat transfer coefficient varies from 2.5 and 500, so it's a wide range. So based on that, I decided to make some experimental tests, varying some conditions, to analyze the behavior of the heat transfer coefficient, to measure and analyze the behavior. So to begin, what is thermal convection? Thermal convection is a heat transfer process involving a fluid in movement in direct contact with a surface at a different temperature. For example, the air in direct contact with a hot surface tends to heat up, so this density becomes lower, and this changing in the density causes some circular movements that is called circular convection currents. So these convection currents will occur until fluid and surface reach the same temperature. So when this happens, they are in thermal equilibrium and no more convection currents will occur. The convection can be natural or forced, depending on what drives the movement of the fluid. So the convection is assumed to be natural when only the temperature difference between fluid and surface drives the movement of the fluid. And the convection is assumed to be forced when there is an external action or force that provokes the movement of the fluid. For example, fans, blowers, or even blowing on the hot cup of coffee is a forced convection. The convection is governed by the Newton's law of cooling that states that the amount of heat transferred to or from a fluid is equal to the heat transfer coefficient that was supposed to be a constant, multiplied by the surface area where the heat transfer occurs, multiplied by the temperature difference between surface and the surrounding medium or the fluid, multiplied by the time. So as I said, the heat transfer is very challenging to obtain in the literature because it might vary when we vary the conditions. For example, it might vary when we vary the temperature range, temperature difference between surface and fluid. It might vary when you change the surface area or the surface geometry of where the heat transfer occurs. And it might vary when we change the fluid velocity as well. So based on that, I decided to make this analysis, and I formulated a question that I intend to answer throughout this project. That is, does parameter variation affect heat transfer coefficient? Or, in other words, if I change the conditions, does it impact the heat transfer coefficient? So that's my question. Here I have the functional overview, that is my block diagram with what I did. So the assembly of my project consists of using water and a mixture of water glycol, that is 30% ethylene glycol solution. And I chose glycol because it's a common component that is usually added to water to decrease the freezing point of water. And 30% decrease the freezing point to minus 13.7 degrees Celsius. So these liquids act as heat providers or heat absorbers depending on the operation, if the liquid is cooling down or if the liquid is heating up. I'll explain this later. So before placing these liquids into containers, I heated or cooled these liquids. So to heat, I used immersion water heater, an electric one, and to cool the liquid, I just used the fridge. So these containers here are two different containers with different sizes. I have a rectangular one and a cylindrical one. And I placed thermocouples in these containers. So I placed one thermocouple in container 1, one thermocouple in container 2, and another thermocouple I used to measure the air temperature in real time. These thermocouples are connected to a 4-channel DAC. The model I chose is DI245, that is compatible with the thermocouple I'm using, that is type T, with special limit of error. This DAC, after my measurements are done, this DAC provides me WinDAC files. WinDAC is the software that is compatible with DAC. And these WinDAC files are easily converted to Excel files. So I generated Excel files and I could make my calculations, my analysis, and I could plot some graphs as well to see the behavior of the heat transfer coefficient. And after that, I could make my conclusion and answer to the question I proposed. This is my setup drawing. That is pretty simple, you can see over there. Consists of 2 different containers with different surface area and different geometries as well. So I have in total 8 scenarios. So 4 scenarios for water and 4 scenarios for 30% ethylene glycol. So they are the same scenarios but changing the liquid inside the container. For forced convection scenarios, I used 2 small fans, one for each container. These are the heating and cooling elements that I used. In this case, the water, the electric heater, and the fans. The thermocouples are connected to 3 channels of the DAC. And the DAC is connected to a laptop that also powers the DAC. It's important to say here that for my calculations, I'm considering only the surface of the walls of the container. I'm not considering the bottom, and I'm not considering the top. So because of that, I put polystyrene foam in the base, and I put also styrofoam or polystyrene foam to cover the lid. I also put aluminum foil here in the top to reflect back the heat to the container, so to increase the insulation here. And here I have a summary of my scenarios. There are 8 scenarios. So 4 scenarios for water, 4 scenarios for ethylene glycol. All scenarios here, I use 2 different containers. I have 4 scenarios for natural convection, 4 scenarios for forced convection, and I also have 2 types of operation. There is the operation of cooling down the liquid, so I have a range of around 42 degrees, and I have the operation of heating up the liquid, that I have the range of around 21 degrees. So here I'm testing 4 different scenarios. I'm testing different containers, different area of containers, and different geometries as well. I'm testing 2 different heat providers or heat absorbers, because I'm changing the liquid inside the container. I'm testing the type of convection. So for forced convection, I'm using fans. And I'm also testing different temperature ranges. So I have a temperature range of around 42 degrees and a temperature range of around 21 degrees. Some pictures of my setup. This is for a natural convection scenario. This is the polystyrene foam that I used to cover to prevent the heat exchange in the vase. And this is the foam with aluminum foil to cover the lid. And here I have a scenario for forced convection using fans, 1 fan for each scenario. The speed velocity here is around 2.5 meters per second. I measured with an anemometer to measure the speed of the air. This is the setup overview of my project. So here I have thermocouple 1 measuring the temperature inside the container 1. Thermocouple 2 is here measuring the air temperature, and thermocouple here is here. Thermocouple 3 is here measuring the temperature inside container 2. And I have to make a small hole to place the thermocouple. I covered this hole with cotton and a tape, but it's not showing here. This is a basic wiring configuration of the deck. Basically what I need to know here is how to wire them, the thermocouple, because they have 2 different colors. They have the type T has a blue wire, and they have a red wire. So the blue wire needs to be connected to the positive terminal, and the red wire needs to be connected to the negative terminal. After my measurements are done, this is how the wind deck files, after exporting to Excel, this is how the data appears to me. So this is the relative time, so it means the sample rate. In this case, I adjusted to 30 seconds. It means that I have 1 measurement each 30 seconds. This is the temperature of container 1, container 2 here, and this is the air temperature. From the Newton's law of cooling, I generate this equation here. Basically what I did was to equate the amount of heat transfer Q to MC delta T, and I isolated H here. So this is the equation to find the heat transfer coefficient. The DAC, the file, gives me almost everything I need. They give me the temperature and the time. I just need to calculate the surface area and weigh the liquid here to get the mass. And the specific heat, I got those from the books, from reliable tables on the books, for water and for 30% ethylene glycol. I automated that sheet to give me all the information automatically. I just had to put 3 inputs here, and they give me everything automatically, including the average 8. So this multiple of 30 here means an adjustment of the sample rate, because sometimes 30 seconds is not enough to change the temperature of a liquid. You can see here, for example, that in 30 seconds the liquid didn't change its temperature. So if the liquid doesn't change its temperature, the H it will be 0. So I adjusted the sample rate to a value that could give me a small deviation. Yeah, it could give me good numbers to my heat transfer coefficient. And these other inputs here are the liquid height that is to calculate the surface area and the mass. This mass here is wrong. I'll show you after in my demonstration. Another, this is a graph that the automated Excel sheet plots to me. So this is good for me to observe the behavior of the heat transfer coefficient. And you can see here that the heat transfer coefficient starts to decrease when the temperature gets closer to the room temperature. So that's why I established a cutoff temperature. You can see here, cutoff temperature. So for scenarios where the liquid is cooling down, I established a cutoff of 35 degrees. And this was necessary because when the temperature is close to the room temperature, the variation of temperature is very small. So we could be highly affected by the instrument error, the accuracy of the instrument. Another graph that is generated automatically is the temperature decay over time. This is for container 1, scenario 1, for example. And this is room temperature. You can see that it's almost, it was kept constant. I tried to control my environment. And here I have the results for my calculations. I made two different measurements for each scenario, and I got an average for each scenario. So this is for water, and this is for 30% ethylene glycol. The literature says that the heat transfer coefficient for the air in natural convection varies from 2.5 and 25. So my scenarios for natural convection are scenarios 1, 3, 5, and 7, and you can see that they are all within the range. And the literature also says that for forced convection, the heat transfer coefficient for the air varies from 10 and 500. It's a wide range because it depends on the velocity, the speed of the air. The scenarios for forced convection are scenarios 2, 4, 6, and 8. They are also all within the range. Here I have some graphs to compare the measurements for each condition. So the first one here, I'm comparing the difference, the influence of the area of the container. So I have two containers with different sizes. In this case, all measurements, all calculations for 8 for container 2 presented higher heat transfer coefficient when compared to the measurements, the calculations for container 1. And this is because the container 2 has greater area to mass ratio, which means that if we fix the mass for each, the mass of liquid for each container, the container 2 will have a greater area for exchange heat. So that's why the container 2 presented higher heat transfer coefficient. And another thing that could have caused some impact here is the geometry of the container. Because container 2 is cylindrical and container 1 is rectangular. So the rectangular container has some edges or some corners. And in these edges, the liquid inside has a low mobility. So it doesn't move with facility, as in cylindrical or spherical containers, for example. Another condition that I tested was the influence of liquid properties. So I changed from water to ethylene glycol. And the result was that all the calculations for water presented higher heat transfer coefficient when compared to ethylene glycol. And this is because, I need to explain one thing first. There are two convections going on in my project. There is a convection outside when the air exchange heat with the walls of my container, that is a big one. And there is a small convection inside the container when the liquid exchange heat with the wall of the container. But the ethylene glycol is more viscous and is more dense, and the mobility again is harder than when compared to water. So that's why, probably that's why, the ethylene glycol solution presented lower heat transfer coefficient when compared to water. Another condition that I'm evaluating here is the temperature range. So I have a temperature range that is around 43 degrees, and I have a temperature range that is around 21 degrees Celsius. So you can see here that for higher temperature range, the higher the temperature range, the higher the heat transfer coefficient. So I'm comparing scenario 1 to 3, 5 to 7. Yeah. And this is obvious in natural convection scenarios, but in forced convection scenarios, it doesn't occur. It occurs, but it's not very evident. I don't have a graph here, but the numbers are pretty close. And this is because for forced convection scenarios, the temperature difference doesn't impact much the convection, because the convection is caused by an external force, not by only the temperature difference, as in natural convection scenarios. And another condition, the last one, that I'm evaluating here is the airflow speed. So that one I think is more obvious. For forced convection scenarios, I have at least double the value for heat transfer coefficient when compared to natural convection scenarios. And this is because forced convection scenarios causes the fluid to move quickly when compared to natural convection scenarios. For testing and results, I tested two critical parameters for my project. They are the temperature accuracy and the response time. For temperature accuracy, I heated water in a kettle, and as the water was heating, I measured the temperature with the thermocouple type T that I used in my project, and a digital thermometer with accuracy of plus minus 0.1 degrees Celsius. Oh, and the temperature of the thermocouple type T that I used is plus minus 0.5 degrees Celsius. And I recorded the temperatures and make a comparison later to calculate the error. And for the test 2 that I was testing the response time, I insert a thermocouple into a cooled water bath and in a hot water bath, and I recorded the time that it took for the thermocouple to reach the final temperature. This is the table for the test 1, so you can see that the temperatures are really close. The highest number that I got here, the highest error that I got here was 0.77%. So you can see that they are close, so the thermocouple is accurate enough for my project. And for test 2, these are the response time that I got. This response time is actually the time it took for the temperature to stabilize, because the thermocouple is pretty fast. they reach the final temperature really fast, but it takes some time to stabilize the final temperature. So this time here is actually the time it took to stabilize the temperature. And just to conclude, the coefficient, I could prove in my project that the coefficient, the heat transfer coefficient, indeed depend on specific conditions of the heat transfer process. Forced convection scenarios resulted in higher heat transfer coefficient when compared to natural convection. Higher area to mass ratio presented higher heat transfer coefficient as well. The water presented higher heat transfer coefficient when compared to ethylene glycol because the water is less dense and less viscous, and also the water has a higher specific heat when compared to ethylene glycol. Graded temperature gradients or graded temperature ranges led to higher heat transfer coefficient. And for future work, I highly recommend to use even better sensors such as RTD. We can find RTD that has an accuracy of plus minus 0.1 degrees. I didn't use RTD in this project because RTD is not compatible with the deck I'm using. And I could finally respond to my question. So the project was fully achieved, the objectives were fully achieved, and I could confirm that changing the conditions of the heat transfer process influences the heat transfer coefficient. These are the references I used in my project, and this ends the presentation. For demonstration. For the demonstration, when I got here, when I arrived here, I heated the liquid, I heated water, and placed in 2 different containers, and the containers are used in this project, and they are collecting data right now. I don't know if it's possible to see. They are collecting data right now. Okay, I'll stop the. I stopped the measurement, the collection of data. This is the automated, oh, it's not possible to see. This is the automated worksheet that I prepare to give me all the information I need automatically. Just need to update 3 inputs. The raw data coming from the DAC is in this sheet here. I just need to place them here. And this worksheet here is for container 1. This worksheet is for container 2. Yeah. And here is the sample rate that I was talking about. Let me try to prove that. No. Ooh, great, thank you. This is the sample, the adjustment of the sample rate that I was talking about. So for example, if I put 1 here, this means that I will calculate 8 each 30 seconds. this is the behavior of my heat transfer coefficient. And you can see here the heat transfer coefficient for the first number, for the first measurement is 0 because the temperature doesn't change. So I chose 20 based on all my scenarios. I'm also evaluating statistics parameters such as deviation and standard deviation. So I established a maximum of 20% deviation for all my scenarios. I established 20 because there is one scenario that I couldn't get a lower number than 20%. So this is my maximum. For the cutoff temperature, I established 35 for the scenarios where the liquid is cooling down. So for example, if I change 35 from 35 to 25, you can see some oscillation when it gets closer, when the temperature gets closer to room temperature. So this is impacted, highly impacted by the instrumentation error, the instrument error. So I established 35. What else? Yeah. And that's it for my demonstration. There's not much to show you.
We now have some easy questions for you.
Okay, good. Easy questions.
Okay, I have a question. I recall that you had requested that we order some very specific thermocouple wire for this this project. Can you talk to us about that, about the thermocouple that you selected, the reasons why you selected it, and you had also mentioned that one of your future improvements would be
RTD.
to even maybe make some more changes in that regard. Can you talk to us about that?
Yeah.
Yeah.
The thermocouple I selected was thermocouple type T with a special limit of error. Thermocouple type T usually has an accuracy of ±1, which is high for my project. But the special limit of error has 0.5, so it's the best one for my project. So that's why I selected this one. And another thing that helped me choose this one is because thermocouple type T is good for wet environment, so I can put in the water or the liquid. And the suggestion that I made to use RTG is because RTG is ±0.1. You can find those, but this is not compatible with the DAC I'm using, so that's why I'm not using it.
And in continuing this dialogue here, why? What is the compatibility issue with the RTD and the DAC? Did you look into that?
No.
Okay. I would be interested to know.
I don't know.
We can talk later.
They are compatible with all kinds of thermocouples, but not RTD.
I have other questions, but I don't want to hog them all.
Well, you compared water to a water glycol mix.
Yeah.
Where would you typically see water glycol mix being used?
Usually in solar heating systems that use water containers as heat storage in cold countries, like Canada, for example. We don't use that in Brazil. Yeah.
Yeah, thank you.
Yeah.
I was wondering about the first test.
The first test?
Yeah.
Oh yeah, the first test.
Okay, bring us
Yeah.
to the first test slide, please.
Maybe I was,
Need some coffee?
So for your temperature accuracy test, which device was more accurate? The thermocouple or the digital thermometer?
Digital thermometer. I used the one from the lab. It was plus minus 0.1 degrees Celsius. And my thermocouple is only 0.5. I had to make an adjustment in my thermocouple as well. In the DAC, I changed the offset, the 0.5 for my measurements. so they are pretty close.
One other question is, can you go back to your actual question that you asked at the
Oh, yeah.
beginning? Yeah.
Oh, here, in the end. It's a little confusing, the question, right? Yeah, because I elaborate that.
So, like the parameter you changed, basically the area?
The area,
thing, yeah?
the temperature range,
Yeah. And that's it.
no, the liquid,
The medium.
the medium,
Yeah.
yes, and the airflow speed, natural and forced. So I changed 4 parameters.
That's good, yeah.
That note, would there be any other parameters that you could test in the future?
Yes, I would like to cause some agitation. Agitation, is that a word?
Agitation?
Yeah, okay.
Yeah.
Inside the container as well, and test it. I could have tested different speed at full speed. I tested only one speed. So
Like
but
airspeed?
yeah, the
Yeah.
airspeed, yeah.
Yeah.
But I tested only 2.5. But I could have tested more. But it would be more scenarios to test.
One thing I was wondering is, maybe this is something else, this is another variable, but you talked about the use of foam insulation
Yeah.
and also the use of aluminum foil.
Yes.
Yeah. Did you consider what side of the
The
foam to
aluminum?
place the aluminum on? Was that part of your consideration? And do you think that would make a difference in the outcome?
It could. I didn't.
What?
No, I didn't. I didn't.
On what side of the foil?
For the foil.
What are the-
I used the side that we use because I used regular aluminum foil.
Yeah.
So
How did you decide what side to place the,
the,
like
the
what side of
that
the,
everyone uses. I don't know.
what do you mean by that?
When you cover a food or any,
Like what I mean is which
I know
side
what
of
you
the
mean, yeah.
which side of the foam?
I know. Oh, the side of the foam?
Yeah,
Oh,
yeah.
not the aluminum.
Yeah. Well,
What
that's
side of the
actually
foam?
another good question though.
No.
Yeah.
What side of the foam should?
Yeah, the upper side or the underside?
Under. Yeah.
So you had the foil against the heated surface?
I can show you. It's like,
Yeah.
yeah.
So you
So-
had the reflective surface
Yes.
against the
Yeah.
against the heated.
Yeah, so
Right,
the
right,
heat
yeah.
reflects. Yeah.
And do you think
Which
that's
the aluminum it would.
do you think that's the preferred way or on the other side?
I think so, yes.
I'm just wondering
Oh, yeah.
if there was some method to that, or like if you were did you actually think about what side of the insulation to put the foil on, or was it not a thought at all, or and would it change anything?
You mean to put the
Yeah, like-
phone and put the aluminum?
Yeah, would it make a difference?
I don't think so. No, maybe it would. When the heat reflects back, it actually doesn't reach the foam.
Right. So
Yeah.
so if you're allowing the heat to transfer through the foam and then reflect back through the foam, would that be less effective, I guess, at reflecting
I
the heat,
guess so.
or I don't know.
I
Thought about that.
I guess so. I don't have numbers, but yeah, I guess so. Yes.
Yeah, I didn't know either, but maybe. Let's see. What does an anemometer measure?
What does it measure?
Yeah,
Airflow speed.
just speed.
Yeah. Just the speed. For, oh, yeah, the one that I got just measured the speed.
Yeah, yours doesn't measure direction.
No,
Okay.
just the speed.
Usually they do.
Oh.
So I noticed
I
you
got
guys
you
used the
point.
two terms speed and velocity interchangeably in the
Yeah.
presentation. I don't know if that was intentional or not, but
They are
what-
different?
What is the difference between speed and velocity?
I didn't know. For me, it's the same. Are they different?
Yes, they are, and that's what I would like you to answer.
Oh my god, I don't know.
Okay.
For me, it was the same.
So, speed and velocity differ in this way, right? Is that,
Oh, one takes into account the direction?
right?
The velocity, probably.
So therefore, velocity is,
So it's speed.
it's actually a vector, right?
Okay.
Yeah.
So I measured the speed.
You measured the speed
Yeah.
because the direction wasn't
Yes.
important in your
Yeah.
case. Yeah. Most anemometers, well, a lot of anemometers are used in weather situations, in which case
Yeah.
the direction would be important. Right?
Okay.
Yeah. Anybody else?
You mentioned geometry as a possible control variable there, and kind of in conjunction with the surface area of your
Yeah.
containers. How would you better test geometry than perhaps the setup you have right now?
Could you repeat your question?
Okay, I'll rephrase that.
Yeah.
How would you isolate geometry as a control
Oh,
factor?
How could I have done that? I could have chosen two containers with the same size but different geometries. But I didn't. So they are together in this case. I can
again-
dissociate them.
More than size, specifically you're looking at
Yeah,
surface area.
yeah. But I think the impact, the higher impact is the size, not the geometry.
Do you think that the humidity can affect the
The-
heat transfer?
It might, but I don't know. The humidity? It might, yeah, I don't know.
What
It
occurs?
could.
What occurs to the air as the humidity increases? What's actually happening?
It gets more dense.
Yeah, it contains more.
Probably, yeah.
more water molecules, right?
Yes. It could, yeah, it's more dense.
So what could that affect?
It could affect. It could affect the convection currents.
If the water, if the air is more moisture laden, what property is reduced?
What property is reduced?
Or what action is reduced?
Well,
I notice it when I'm sitting outside on a very humid day. I notice that my body's
wet.
cooling system doesn't work as well. Why is that? I feel hotter. Why?
Yeah, it is.
Why? On a humid day I feel hotter. Why? I'm not actually hotter, but I feel hotter.
The water molecules retain heat.
Maybe I am actually hotter. Yeah.
They have the capability of retain heat easier. Not easier, but they can retain more heat without changing its temperature.
Why is my body's cooling system not working as well on a humid day? Maybe that kind of goes along with your question. So how do our bodies cool us? Like how does our body's cooling system work?
This is biology.
No, I know, but it's all the same. It's all related, right? So what happens? We're perspiring, right?
Yeah.
And how does that cool us down? If the liquid stays on my skin, am I getting cooled?
You are eliminating heat.
Yeah, how's it happening?
through your wet, your sweat.
Yeah, and then what needs to happen in order for cooling to happen on the surface of my skin?
Dry,
Yeah, it has to dry, so what's that called? There's a word for that, starts with E?
starts with E.
Yeah. Ends in T.
Okay. Evaporation.
Evaporation, right? Has to happen, right?
Yes.
So back to,
Okay.
this
The
is Al's
question.
question. If the air is more humid, how does that affect evaporation? Remember, she asked this question, not me.
Yeah, I know.
It's harder.
We're just trying to direct you there. So how is the rate of evaporation affected if the air is more humid?
No, can you help me?
It's your time to shine.
Okay. Oh my God.
If the air has more water in it, is it going to be less able to accept more water?
Yes.
Yes, right?
Yeah.
So therefore, now answer her question.
I am?
Will the humidity affect,
Yes.
right? Definitely, right? Yeah, definitely it can. Are we at time yet?
Yeah.
Okay.
Thank you.
Thank you. Great question. See that? Official question answered now. No, it's just maybe they came when you were students. They came again this year, but it's all blurred
Eu acho que a festa
Não, mas você já tinha escolhido. Mas ele não aceitou?
So I'm just going to write it down. I didn't like to make mention of the people who come.
Mas ele apareceu mesmo.
seleção natural.
Right, I get that.
Não, eu lá onde conheço lá, mas ele veio
It's all like he's working with you guys. Yeah.
queria deixar no carro, mas eu
On that exact note, we got
Congratulations.
Ah, eu bebi.
It's like that, right? Yeah. Okay. The new model is a two-term model running from September until April. So basically ending where the winter term always ends at your spring term. So there are several challenges. Well, it's on tight because there are things that have been removed. So the whole model is to teach less, but offer post-diploma options or programs. So like a lot of the stuff that would have been considered to be more specialized will have been removed from the program. Okay, and therefore, if you want to know more, enroll in a third year, basically, or enroll in a post-diploma program. Notice in that one. Yeah, which would be then we will be able to then teach telecommunications again. Maybe like it's all still under development, right? So maybe it'll be automation specialist or whatever, right? Like, and then it'd be like a full year, not full year, but another 2 terms in the third year, whatever, that would contain some of those more specialized courses. So I think what it's doing is making the 2-year program more general, if it wasn't general enough already. And then specifics added on after, if you want to, kind of thing.
When's that start? It's already started.
It started in the first year this year.
You'll have a summer semester this summer.
So so what I was saying to Andrew is the 2-year program that was when you took it and when Andrew took it was 3 terms, like two long terms and a short term.
Right.
Yeah, and now it's going to be just 2 terms.
Oh, okay.
Okay, so 2 terms per year.
Right.
So to fit everything in, it just means that some of the more specialized content is not there anymore, and will be offered as a 3rd-year post-diploma program.
And we had a package, they mentioned that there's courses year round.
Yeah, so what that means is that the normal delivery flow would be from September through till the end of what would have been the winter term for you, which will still be the winter term, but no spring term. Okay, and so then if you passed everything, you come back in September of the 2nd year, and then take 2 more terms, like fall and winter, and then you graduate. However, if you do not pass everything, those courses are taught again in the spring and the summer, because the technician program is running then. The technician program actually starts in January, actually, and they graduate, or they finish in August. So if you miss courses, you can start picking them up. Like, let's say you missed a fall term course, the exact same courses, because the technician program is basically equivalent to the first year of the 2-year program. You know, they start taking those courses in January, and so if you miss some in the fall, you can retake them in January of your term, and then you can retake those courses in the spring. You're not able to years. Yeah, so it makes it so they can kind of you can pick up that those extra courses and still be on grad track by the second year if you read the workforce. If you realize that, like we all came to that realization, that, oh man, I need to work a little bit harder. But if it was too late for you and you already missed the get back on track for a few guys that happened to, right? So that's a very common thing that we see. Yeah. And so this model is going to help with retention of people. So it's good. It's 2 years. So it's 1, 2, or 3 years, depending on how far you want to go with it. If you want to graduate with a technician certificate, you can do 1 year. If you want to graduate with a technology diploma, you can go 2 years. And if you want a post-diploma or advanced diploma, you can go a 3rd year.
Would that 3rd year count as an additional, say, year or?
Yeah, well, I don't know. It depends on who you talk to, because if there are articulation agreements with other universities, then yeah, those credits will transfer, but it depends on how they choose to accept those credits.
And then you get the various, like your electronics versus, say, robotics versus whatever programs as well. So,
Yeah, it's interesting. It's gonna be interesting adapting to all this. Yeah.
Well, you kind of overrun.
What time do you guys arrive?
Yeah, because last week in this meeting, wasn't happening yet. When Dennis was here, he wasn't present.
It was very quiet during that like this morning. Very quiet.
Not
You could hear, oh, I could hear during
Yeah.
I didn't notice that. Oh, I didn't notice, but I noticed during the presentation.
We're all working on something
Yeah, she messaged me. She's like, wait, yeah. She's like,
Oh, yeah. Okay. Open the box. Okay, we're just about to get started with our next presenter here, and before we do, I just wanted to say thank you to MCW for bringing people here today from industry to participate in our symposium. In the middle over here on the right, we have Andrew Jardine, Andrew Lavoie, and Stephen Perry. I know for a fact that Andrew Jardine and Stephen Perry are graduates of this program, so it's great to have them back here. And I'm not sure where Andrew Lavoie is from.
I'm wrote from back in 1978,
Are you from? You're from this program too?
electronic.
These pictures on the wall.
Okay. So all three of them graduates from this program. Okay, so it's great to have them here. We know that you have busy schedules, and we really appreciate you taking your time to attend. So without further ado, we have Mr. Jose Olimpio D.S. Filho, right? Okay, and his wireless temperature monitor.
Okay, thank you very much.
Okay.
As George asked for a warm good morning you. Not so warm as George, but okay, thank you. Okay, I will talk about my wireless temperature monitor, and I have to say some history of how this project became that way. I'm an electronics engineering technology student here at NBCC, and it's hard, it's not easy to be that. And this project started as a weather station. At the beginning, when they showed us some projects that we can choose, the first one of the list was weather station. But I was worried about the price component. In my mindset, I used to work as cheap as possible. Well, I'm from Brazil, you know, so we have a lack of components, we have inflation, we have also shortage of chips and everything. This is not normal life there. And we have this also here, inflation, lack of components, and that was the scenario. So I took the weather station and get some components out of that. The anemometer is expensive, $120, the cheapest one I found. And let's take the things out, and it becomes only a temperature measurement. Well, temperature measurement is also easy to find in the market. And it will be not so good to show here only one project measuring temperature, because we had a practice on a lab, in one of the labs using this. We used there the LEM35 component. So to become a little bit more challenger, I put this wireless. Oh, I want to show the temperature in a computer. That's a little bit challenge for me, so let's do it. At the very beginning, on the first EDR, I was there with Mr. Metcalf and Mr. Broad. My advisor, Mr. Joha, was also there. And, you know, I showed my proposition because I had one thermometer with my stuff at home. I could use that. And the moment I showed this to Mr. Metcalf, he took his iPad, just like that, put his glasses on, and looked at me like that way, and said, "All right, if I were you, I would start right away, man. It's not so easy." Well, of course, in my mind, I didn't believe him. Yeah, of course. But let's take this in account, and let's start to study in the Saturday morning, the day after that Friday, EDR Friday. Yes, there is no libraries to work with this device. I will explain you the trouble where I was in a few moments. So, to explain all those things, I have made this agenda: introduction, functional review, technical description, some tests, results, conclusions, references, and so on. After many feelings, philosophical stuff, and decisions, that's the aim of my project? To show temperature, is a temperature system, enabled to show the results in a web server accessed via Wi-Fi. And I put that phrase here, using a modular approach, which means I could put more things on it. Of course I didn't, because of lack of time, and I have my own excuses. But it's possible to do. It's possible to use this in further projects. Okay. So the first draw I made with the function overview was this one. And that's just a scale problem. Because this sensor I showed here is this one here, is this size. And the project looks like it's bigger than the sensor. But actually, you can see this draw here and see how the system works. It's, is this sensor here, the measurement system, connected to a box. You have on-off, a light to show, a LED to show it's on or off, and wireless systems to show in a computer the value of the temperature. Pretty easy, pretty straightforward. That is how this project became, this small black box there. And that's one part, and the other part is a website where I can show the temperature, what looks like that, a small, simple one to show. So, the functional review of that, this is the block diagram, is composed by 4 blocks. The power, which provide 5 volts and 3.3 volts to the system. And the system is a measurement system, a microcontroller, and Wi-Fi module, which is responsible to send this through a web system in a way. Zoom it, we can see the main blocks of it. And I have 2 contests here. The contest of hardware, which are the components and the PCB and all this stuff, which is these 3 blocks. One is the DS18B20. This is the thermometer I was talking about. I had this at home, and I look at this. Oh, it's pretty easy to do this. This is a digital thermometer with a lot of characteristics. I don't know them by heart, but it's one wire protocol. This works with one wire. That means I can send information, I can receive information from this device, and just one wire. And 12 bits resolution. I can spend the maximum of 700 milliseconds to communicate with them in the worst case scenario, which means if we have a lot of devices connected together, because this device here has this feature, you can put a lot of devices, multiple devices in just one wire, and you can address each one of them. Of course, I was there looking at this data sheet, and oh, I'm good. I'll use a library, put in my C file, and ask the methods, the functions with this library, and I'm good to go. Minutes after Metcalf told me, oh, if I were you, blah, 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 I wasn't sure about that. There is no such a library able to work with the microcontroller that I had. And I told you, lack of components, shortage, this is my mindset. I would not buy another microcontroller. I'm stubborn. I will do this. So I had to build this library by myself. Of course, I had some help from a lot of people. but I did. And this DS18B20 is also a device that has a possibility to work in multiple functions. And alarm, we can set alarm on it. And if we use this device with all the features it's possible to do, 750 milliseconds to achieve the value from each sensor we have in our network. I had done one. But 750 milliseconds, maybe it's too much time, but actually for temperatures changing is not so complicated. When we are measuring some RPMs or some other kinds of physical stuff, it's more useful to have faster components. But in this case, it's good. The second main component of this project is this one here. It's ATmega T28P. It's a very well-known microcontroller, RISC architectures, IDE, and I'm using the DDR characteristics, the data directory register, in and out, to communicate with my DS18. That was the idea. Inside the program, inside the C program, I will use the information I achieved from the temperature sensor. The temperature sensor. I will check this value here, and I send to the Wi-Fi module, which is done by this device here. This device here, ESP8266, it's a Chinese one, but inside of it, it has a microcontroller called LX106, which is made by Tensilica Extensa, an American company. This microcontroller, it's more advanced than my ATmega. Has a lot of features, 16 bits, 80 megahertz, and it's possible to do access point, to web client, all the stuff on it. Even web sockets, we can do it with this component. So, in this scenario, I also have another contest, which is software contest. This software, I had two of them. Control. I have one software here, C language, and I have another one here, C language as well. It's possible to use Python in this Wi-Fi module, but I didn't use because it will take a long time to install all this stuff. But we have this contest here. Those are the flow charts, I know. You cannot see. This is the flow chart of the temperature monitor, which is run in my ATmega. And this is ESP8266, runs on the other module. The main things that we can see here, both works the same. We have a settings at the beginning, and we have a loop. And in this case here, the ATmega T28P, I had to build the loop using a while -1 and keep this while running. And this device here, we have two modules. We have a setup module, which runs in the beginning, and we have this module here. Oops. This module here, which comes a loop and keeps running and running and running. Talking specifically about the software in the microcontroller unit, I had to talking with the DSP, which use my one-wire protocol. I have to convert the binary data received from the sensor to float number. Float because I want to work with decimal values. At that moment I wrote this, I didn't realize I would have problem with negative numbers as well, but I solved it then. 12 bits is the full capacity of each one of these sensors. And I would use a serial WART feature, which is a hard protocol inside of Atmega that I can talk with the ESP8266. It's this one here. And the second software I have on the Wi-Fi module, I will do the following. I will receive the value from microcontroller, enable its web server, connect to a router, create a simple web page, update every 5 seconds to show it's updated, it's working, and I list a loop with 10 lines only to show that my measurements are happening. About the technical description, which are the next topic, we have a user interaction. Actually, it's not so difficult to use this device. We had here this device with a on-off switch, a small LED to show it's working, and a web page. Here I put in my fridge to measure. During this time I had these values here. So let's go to the circuit. You can see in this circuit the same draw as the block diagram. You can see here the power supply, the temperature module, the sensor, the Atmega, which is my microcontroller, and the ESP8266, which is the device responsible to send information to internet. Let's go in each one of them. It's a pretty simple power supply. I have one 7805 to supply my 5 volts, and I have a 3.3 using LM1117. The thermometer is also easy to connect. I have this. This thermometer has only 3 wires: the VCC, ground, and data in, data out, which is represented here by this DK pin. DK will send the information to Atmega 320p. This information here will go there using the one-wire protocol. This is the place that I told you. We can put a lot of devices here. If you want to make a profile temperature of whatever furnace, for example, if you have a huge furnace and you want to do that, you can use this protocol, just one wire connecting all the sensors there. Of course, for a huge furnace, you need to use a thermometer which can range this kind of temperature. Mine is only 155 degrees Celsius. The microcontroller unit is Atmega 328. Receives the temperature, the information of temperature from the DS18S, DD18S, on the data register number PD2, DDR2. I'm using this one to communicate. Inside my program, I will receive the numbers. I receive the digital numbers, convert to float, convert again to a character, and send this in the serial port here, pin number 3, which is a WART. You may ask, oh, why are you not using the other pin because watt has 2 pins. Well, I don't need any information from the other device, so I do not use it. So I have only one connection. I will send information, text information, from this ATmega to my ESP. Here is my Wi-Fi module. Again, I received the information from ATmega. I had a look, I will build the web page. We'll keep 10 numbers there and we'll build a line, a table with these 10 measurement values and stay showing there again and again. And this LED here is this one here, which you can see. You cannot see, but it's here. This LED shows the system is working, but during the process of startup, I also do some blank tricks just for me to know that my system is doing well. And also there's an antenna here, Wi-Fi module, send this information to the web. So the integration test. I have 2 tests. One is this integration test, which I name it as a comprehensive test to the entire system. Well, I'll show you the system working. It's pretty good. I turn on the device and I see the temperatures there. And I can measure different values of temperature to show, oh, it's really working. Some negative numbers, some float numbers, and I can see the system is working. My LED is on, and I put this on a fridge, my fridge freezer, and I did some print screens to show that works. You have to believe that, my print screen here. Which are those. This is the device, I put that, I close the door, and I start to measuring. The moment I started, you can see here, it was 23.4 degrees, and pretty much the same because every 5 seconds this system built this table here showing the temperature. And I can go, the temperature was decreasing minutes later. Now it shows here 3 o'clock p.m. Some seconds later, 3:01, 3:02. The temperature was going down. Oops. So I let the device there for a while, just collecting some temperatures. And that's it. I took the device out of the freezer and the temperature started going up again. The other test I made was a calibration test. Actually, there's no way to calibrate because it's calibrated from the factory, this device. But I call it that way to be sure that I was measuring the right values. The calibration test, I checked these values. We're using an unprobed TMD50 in the lab here. I also use some liquid, freezing spray to achieve the negative temperatures to doing this test, and works fine. Here is a table that I built showing some results. We got here values from my wireless temperature monitor, the same temperature I got with the M-probe, and the relative error I got. The average of them is 2%. And this negative here means the temperature of the M-probe was less than this one. Only this negative number only shows the direction of the difference. But it's pretty good considering I'm using this kind of lab as a monitor. as a checking, it was okay. I also did some ping tests to see if it's working. It's working, no problem at all in my network, works very fine. And we finished this presentation here with some conclusions that I made. For me, the project works satisfactorily. The one-line communication protocol worked flawlessly. Of course, I don't need to address any device because my device has only one thermometer. I have some delays during my process because I had AutoCAD issues. Many people knows about the problem I got. I lost my license because NBCC sent my document. I was supposed to work to study here by December 22, and between Autodesk and Share ID, I lost my license and I decided to use KiCad to build my PCB from the scratch. I decided to learn KiCad by scratch. I had a problem during my project because I received 78.78505 and LM1117 in the different packages. And my fault, I didn't pay attention, and I burned one ESP8266 with 3.3 volts, and I wasted 5 volts on it. And for my own development, CSR, I think it's an important tool, works and contributes positively, works good. And the problem is we saw many people struggling here during our own projects. Every one of them has our trouble to make these things happening. But I think everything is very good. Some improvements that I can do with this project. I have the size of PCB. I can shrink this device. I can configure some graphs, some other stuff here, save file, CS file, so on. And I can also use WebSockets, web servers as well. And I use these references here during the process of my project. So, now I'll show you my demonstration. Or should I say, this is the end of my presentation. Okay. Actually, during the whole time the system was here working. It's like the drawer, it's a small box, black box with temperature sensor here. And let's see how this works in the website. How do I send it to that?
Exit the PowerPoint.
Yeah, I
Yeah.
accept.
No, it's still on the screen. So
Yeah.
there you go. And then it'll,
F1 again.
no, it'll,
got it. I was showing you and you didn't saw it, and I was here. Now you can see the system working. Let's go to the system and hope it works. Okay, this is the temperature now, 20. Here it says 20.5 and show here 20.7. And every 5 seconds we'll keep updating. I will use some idea that I got from John. Let's heat this up and hope this works. And hope I have this working fine to give to my wife and my daughter back. Ooh.
Yep. Looks like it's coming up from the bottom.
Yes, yeah, because I will. The system is using the.
Oh, there's like 10 positions that just fills it in the circle.
Yeah, it's a circular. It's starting
Okay,
5
okay.
5 in, 5 out. And well, after that we have another thing. Oh, something that I could improve could be this. I should, if I turn on off the device, it will try to connect again and will not work, of course. And this is some things that I could improve. I maybe put here, at the moment the system detects, oh, the device is not working, I could show, oh, it's not working. That's, stop that. Instead, the system gives you this, this result. This can be improved. If I turn on again the system, if we are lucky, few seconds or a few minutes later, I don't know how long, it will be back on the air again. Or if I can press F5 here, which will update, and show the values, the temperature measuring again.
Good, thank you.
So, starting again, the values.
Thank you.
Thank you.
You look like you don't have questions.
Yes.
Want to start off?
Go ahead, yeah. Could you bring up your schematic, please?
Right now it's
You know, there's a message here, you know. Please do not ask many questions.
Yeah. That's what that acronym means.
Which one?
I want to see the input, the power, yeah. I noticed your L7805 didn't have an input capacitor. Why didn't you have an input capacitor
Well,
here?
actually, the input capacitor is placed near the 1117.
So
Yes, you see one?
they're sharing an input capacitor?
Yeah.
How is that possible? Like what about your PCB design is making that possible?
Because the pin 1 is connected with pin 3.
Are they, you didn't show us anything about your PCB,
yes.
did you?
Yeah, no.
No, so I'm wondering physically, what is true about, sorry, I'm hijacking your question. Physically, what's true about your PCB layout that allows this?
Well, I can show you, we can open it here.
No, I don't wait, take
But,
time to do that right now.
It's connected here, look, 1
Okay.
and 3.
I know
So
they're-
if this capacitor, the positive is connected here, I think.
I know they're connected, but that doesn't answer my question.
I didn't get that, sorry.
I'm wondering, what about the layout allows you to think that you can use one capacitor for the 2 input pins?
But in my point of view, the layout has nothing to do with the electrical
It does.
properties.
It definitely does. It's-
Because they are
in
near
the data
each
sheet,
other.
it explains that it does, right?
Hmm?
In the data sheet for the 7805, as an example, there's quite a bit of explanation, paragraphs on this, the importance of this
Yeah, I
input
got-
capacitor.
I use one configuration on page 7 of the Texas instrument example, and there's no input capacitor. I put this one for the LM 1817, which was in the page 14 of my
Yeah.
on my
So,
that data sheet. So I just trust them,
So
and
what-
I use that way because of that.
so what's true about the layout then that would allow you to forgo that, input capacitor on 7805?
No, this I don't know. I just use it the way it's in the data sheet.
Well,
Well,
just because you see a diagram in a data sheet doesn't mean it applies to your situation.
Yeah, but the moment I was developing these things, a lot of things doing at the same time, works fine. I saw there, it's okay, I didn't.
Yeah, well, it works
pay too much
fine.
attention.
Right now.
Yeah,
But back to, I think that's really the nature of the question though, is if it does work, why does it work? And how can you get away with
but
C1?
actually, I don't think there are so many issues here because my device consumes about 50, less than 50 milliamps when the maximum power, which is the moment it's updating the web server. At that moment, consumes only that. So I don't.
So are the two regulators located physically close to each other?
Yes.
See, that's what we're getting at here, right?
Yeah.
Maybe it's possible that if the trace length between the two components is very short, you can get away with the one capacitor.
Yeah.
But
Yeah, I follow the guidelines.
I just wasn't convinced of that because I didn't see your layout, so I don't know.
Okay.
So I think it's something that's, I don't know whether you overlooked it or if it was intentional.
Well, maybe I'm lucky
Maybe, yeah.
because it will.
The other thing,
I have never failed on that.
yeah, not yet. The other thing too that is recommended in the data sheet, at least for the 7805, I'd have to look at the 1117 to see, but is what else is missing here between terminals 3 and 1?
Actually, I copied this one, as I told you, page 7.
Yeah, I know, but
I look
Yeah.
at that, the simplest one,
No.
the power, the power
I know
needed
that.
was less power, I saw
But you
the
can't-
simple configuration, and I choose this one.
you can't just look at a data sheet and not read the text that goes with the diagrams, right?
Yeah,
The
but
di-
they
the
showed it-
diagram
they
is
showed
given.
it.
But if you look further, if you read further, they say that a diode is recommended or required there. Why do they say that?
Yes, recommended to do the flyback, the flyback diode.
No, it's not flyback. That's not what it's there for. Why is it there? Why does the data sheet, why is the data sheet so strong in recommending that diode?
I don't know, I don't know.
It's really important. Okay, well. He doesn't know. Do you have another question?
No, for that, no.
Okay, maybe the next part of the schematic?
I'm good with the schematic.
Are you?
Question?
Yeah, you could take us to the, you have a command
But
prompt.
I'm pretty sure,
You,
for this kind of device with so was less consumption of that, we don't need this such a, to be worried about. When we have a lot of process, we have a lot of more. Okay.
So you had a slide where you had a command prompt. Can you bring that one up?
Which one?
The command prompt. You had a command prompt slide. Command line interface.
This one here.
Yeah. What class of IP address is in use there? And explain why you say that.
The class, I forgot the class. I know we studied this.
Yeah, it's something
Few
that I
months ago,
think
yeah.
you definitely should
And
know
this-
if your,
yeah,
if your
this
project
one-
involves IP addressing and you studied IP addressing, you should be able to tell me that.
Yeah, I use the default configuration.
Which is what? Which the default configuration uses what
This
class
is
of IP
for-
address?
Yeah, but this one is only for, to use the 50 numbers maximum, so it may be this class A. I don't remember that, I know that. I know this is something that we have to do when we are managing network.
What does the, how about this question then? What does the -T switch on your command do?
This one keeping the pinging over and over without stopping.
Without it,
That's the reason I did that, because
Yeah.
without the T,
What
it
does
would
it
be
do?
only 4.
Okay, good. What about, you have, like you say, a persistent pinging happening there, and if you look at each line, what does the, let's see, after the IP address, there's some information there. What does the TTL value mean? What is that telling you about that ping request?
So that's, we have here the number of bytes that I sent, the time I achieved, and the TTL will see the how many hosts that I can, how many hosts or devices we can go through the network to have this number back. In this case here, there's only one router, simple router with this device. So only show the phone number.
So, so say that again, that the TTL value means what?
This is the number of hosts that I have to achieve
Number of,
through the networks.
number of hops, right, through the, yeah?
Yeah.
And so, what does that mean then?
That means if we change.
What happens if that number is exceeded? Through your ping operation?
The ping will not be received, or the time will be too long.
What-
And the ping will.
What occurs,
expire.
what occurs if this ping goes out into cyberspace? Goes through 255 hops, what happens on the 256th? What does the router do at that point?
You to ignore that. And from my point of view, when I do the ping, I will receive the answer the host was not found.
Right? So the router will discard that packet
Yeah,
at that
discard,
time, right?
right, discard it.
Yeah. Okay. Any other questions?
The ESP8266, did you program it yourself, or did you use the existing command set up?
No, I programmed it by myself.
Okay, so you didn't use any of the AT command features that come preloaded on it, or any of the base firmware?
Yeah, those AT commands are in the settings.
Okay.
The settings I use the AT command to start, and also AT commands to start the web server, and to configure the serial port for WART, because I have to receive information from WART during the same time as I'm building the web server. I have to do all this in the setting parts. And the program, during the program, I only took care of the web page. Managing the values from WART, of course.
Would have been really nice to see.
And this can be used on in the first day of presentation. Or João was showing. You asked McGregor. You asked about a possibility to have the historical values from the temperature. This device here can be used to integrate to that one. That you can use that value there, the same atmega, and send to this and create some CSV files and use this to monitor the temperature of the device that he was using.
I just want to add to that, since we're kind of talking about the code. This is mainly just a comment, not really a question, but throughout your presentation you mentioned that you had to build your own custom library for a certain component to get it to work.
Yep.
You were showing a lot of pride in you writing that, but it would have been nice to see
Oh, actually,
that.
yeah. Look. In here, let's show. Like this. During the process, I'm not that organized, okay? I learned this with using it. Look, here, I don't know if you can see. Maybe this way is better. Yeah. Look, this is the flow that I have to use to communicate with this device, with this the DS18B20. I have to it's one wire, so I put in the line, when I turn on the device goes 0 immediately. And I have to give the device a 408 microseconds pulse. And so I measure that, I put a delay and send, go up during 1 microsecond, and go down and change the data direction register to be input instead of output. I change this and waiting for answer, which is this answer here. It's a number CC that the device has sent me. Oh, I recognize you called me. And I send back again to start in the process of measuring. And I keep doing this the whole time. It's pretty easy when I talk. But to do that, I have to build all those numbers.
It's fine.
Yeah, you know.
We're up on time here, but it would have been nice to see some code there. You mentioned it a lot, but it would have been nice to have that in your presentation.
Oh, I'm sorry.
Thank you very much.
Yes.
The main thing is, work itself, in a company, for example, it's harder. You are focused on at the same time.
We both did development projects outside of NBCC. There's a lot more work as we go into a lot more depth.
Yeah, it is.
People want to
Yeah, I used to work in a steel company. It's pretty hard to get comparing to here. Here it's more.
It really just wants to know.
I just don't want to see kind of excuses and stuff anymore because I learned more on the job than study and just as much on the job.
As a student, you can only go so far, right? When you work in it, you're actually reading the details and data sheets, you realize that every phrase is there for a reason it
Like this?
Yeah, so I was at here. The moment it seems I
Yeah, that's true. So now I'm lost by a paper. That's what I'm gonna do. So.
Yeah, I have a timer here.
Everybody's yeah, well, until I noticed, I'm like, uh-oh. So then I skipped hers. And so now basically hers is here. And
Maybe I can
wait now.
Great.
This would be in the
Right, and
phone,
they're just
yeah.
saying like good job or giving me a time. Yeah. Right, yeah.
I was pretty sure she wasn't on there. Okay, so now this is yeah. So is her name pronounced the same as yours? Hers is actually Leo. Leo?
Oh my god.
Oh, Tilson. Yeah. Is it over there that or today?
Yeah.
You're gonna be there.
You know, it's just simple.
No, it's a Tilden.
Getting the dust in.
So our next presenter is Ashley Edmonds, and she'll be presenting on her dual-axis solar tracker.
Thank you. So as Mr. Broad stated, my name is Ashley Edmonds. I am studying in the Electrical Engineering Technology program here at NBCC Moncton. I decided to take the Alternate Energy Systems pathway, and for my senior project, I have chosen to design and build a dual-axis solar tracker with the guidance and help from my advisor, Mr. Dennis Legier, who was super helpful with the design during this project. An overview of what you can expect during this presentation. So I will provide some background on what solar trackers are, specifically a dual-axis solar tracker, which is the purpose of this project. We'll go into some concept drawings, how the project works, with a functional overview looking at the block diagram, mechanical drawing, and also the technical schematics for my project. Then a look at the final build, and going over the testing I conducted, as well as relaying the results from those tests to you, and gathering the conclusion that I gained from the project. So a little background on solar trackers. I'm sure by this point all of you are familiar with photovoltaic panels and solar energy. As it comes to PV panels, there are fixed axes or tracking. When we get into the solar tracking, you can have either a passive tracker or an active. This would be classified as an active tracking system because it uses electrical components. When you get into solar trackers, there's also the difference between a single axis or a dual axis. So this project is a dual axis. As you can see in this diagram, there are 2 points of movement. The first point of movement is the elevation axis here, which adjusts, I refer to it as the tilt angle and the elevation angle. For me, they're interchangeable terms. And the second point of movement is the azimuth axis here, which serves to change the horizontal position of the PV panel. So basically it can adjust it, rotating it in either direction, like 360 degrees. Although in reality, it's never going to be required to move a full 360 degrees. It has that capability. The main objective to using a solar tracker versus like a fixed angle PV panel would be to maximize the amount of solar radiation that the PV panel can capture, and then it relates to a higher energy output. That's the idea, higher efficiency. For the purposes of my project, I wasn't so concerned with how it performed and like the amount of power that was captured. I just wanted to, it was like more of a proof of concept project to see if I could design and build a dual axis solar tracker that would be comparable to what you find maybe on the commercial market, but on a smaller scale for what I was applying it for. So the reason I chose to do the solar tracker specifically was because of the camp we have up in Minto, which is outside of Fredericton. We do use a lot of like DC batteries, and we just have a huge amount of like storage banks that we use for the purposes of charging cell phones and tablets when we're out there. Having a solar panel aids in that because we can charge those power banks while we're there and not have to worry about losing access to our cell phones, God forbid. The other idea was there's a lot of shading. Being that it's in the woods, there can be trees that impact the availability of the sunlight that's going to hit the panel. So with a solar tracker, you're able not to overcome the shading completely, but you're able to maximize the amount of sunlight you can capture based on how the sunlight hits those sensors. So that was the idea behind choosing this project and designing it. Now we'll look into the actual concept drawing of the project and what I had planned it to look like in the final build. I did run into some mechanical issues because I do not have a mechanical engineering background. This was all very new to me for the build, so I used what knowledge I had and the resources available to me to do some quick troubleshooting at the end to have it as functional as I could. As you can see in the concept drawing here, the idea was to take a 25-watt photovoltaic panel measuring at 16.5 inches wide and 12.5 inches high. The framing for it, I decided to make my own frame instead of what came with it. The frame that came with it was a very thin aluminum metal, and I just thought, like, with the movement going back and forth, it risks the integrity of the metal and could cause breakage issues, especially with wind shearing and like any possible snow loading if this were to be used in the winter. So for the purposes of my frame, I chose a 3/4 inch aluminum tubing, a little bit more structural integrity for the frame. And the two motors responsible for the movements of the PV panel, the first one is the elevation motor here, which is located, well, depending on how the panel is facing you. If you have the PV panel facing you, it's on the right-hand side. And the azimuth motor is located underneath the bottom shaft, actually, so it's mounted underneath the wood platform that it's mounted on and is responsible for rotating the entire frame. If you look at the side view here, it's a little easier to see where the motor is placed. And so this entire shaft is rotated as the azimuth motor changes. Also pictured here is the electronic enclosure, which contains the entire circuitry of the solar tracker. And is the main scope of my project, is essentially contained within this box. The PV panel and the frame and the motors are, I guess you could call them like tools to like see the functionality of the project. What I was really concerned with was designing a circuit and printing the circuit board and then like to be able to actually have a solar tracker and being able to see if it actually functions. You need to have a PV panel with a frame and motors to prove that. Next we'll look at the mechanical drawing, which is essentially just a drawing of the electronic enclosure that was shown in the previous image. The enclosure that I chose was produced by Hammond Manufacturing. The only changes I had to make was to cut out two holes. The first one here is for the on and off switch on the front panel. And I just chose a simple rocker switch for the on and off switch. It's familiar with people there. I assume most people in this room know how to use it and what the green light on top means. The second hole I had to cut was in the back for all of the wiring to come through. I actually had to make an amendment on this. There's actually two cable glands coming through the back instead of just the one that's pictured here. So the first one contains all of the wires coming from the LDR sensors, and the second one contains the wires coming from each of the DC motors as well as the power supply coming from the battery. So how does the dual axis solar tracker function? We'll go into the block diagram for a general overview of how it's supposed to function and what my expectations were for it. So pictured is the block diagram. We'll go through it section by section. As you can see, it's for the elevation axis and the azimuth axis. They're essentially the same, so I didn't bother, to avoid redundancy, we're not going to look in depth at both axes. I'll just choose one to focus on. They perform in the exact same manner, they're just named differently, and obviously the movement of the PV panel changes accordingly to what axis we're talking about. So looking at the power supply coming in, I chose to power the entire system through the 12-volt DC battery that is coupled with the PV panel. The idea was that instead of using an external power source, you can just power the solar tracker with the existing battery that you're using. Coupled with that is the voltage reference, which will be used in the comparator circuit, and we'll go more into that later. But the range expected for the voltage reference is between 5.7 volts to 6.25 volts. So looking at the first part here of the block diagram, we have what would be sunlight coming into the LDR sensors found for the elevation axis and the azimuth axis, with V reference as well. So these are considered the two inputs and the first blocks for the block diagram. They're the inputting signals that go into the comparator circuit. Each axis actually has two comparator circuits. So I know here it's shown as the elevation sensors and the reference voltage just going into one comparator circuit, it would actually have two here and able to control the H-bridge motor driver effectively. So the two inputs from the sensors and voltage reference are delivered to the op-amp comparator circuit along with the power supply that is fed from the 12-volt DC battery. Once the comparator circuit receives those two input signals, it then delivers its output signal, well actually two output signals, which should be shown here as two arrows, not just one. And those outputs determine how the motor driver will behave. For the purposes of this project, to avoid using like a voltage regulation source and to just keep my supply voltage the same, I chose to do an H-bridge motor driver using components that could handle the 12 volts and the high ampage that the motors have. So the comparator circuit would feed its two outputs, which then gets fed as inputs to the H-bridge motor driver. The motor driver reads those inputs, and its output is the mechanical connection to the DC motors. Again, here is shown with a 12-volt source feeding the H-bridge motor driver so that the components have the power required to function. So a little more in depth on the major components I selected. The first are the light-dependent resistors. The range that I chose were from 8 kiloohms to 16 kiloohms. How the light-dependent resistors work is as the sunlight intensity increases or decreases, the resistance changes. So as the level of sunlight increases, the resistance will decrease. So that means under like the brightest light, you can expect the 8 kiloohm resistance readings across them. And under like a cloudy day or possibly no sunlight, it would be at its maximum of 16 kiloohms. The next most important component in the system is the quad output general purpose op-amp that I chose. The op-amp works as the comparator circuit, and the reason I chose the L2902 specifically is because it allows for 4 channels output. That way I was able to control both the axes with using just the one IC. It made for a simpler schematic and also a simpler PCB design when it came to it. The following components are the BJTs I chose. So I chose BD135 and BD136. They are general purpose transistors. The BD135 is the NPN resistor, and the 136 is the PNP. They were chosen because they also have a wide range of voltage that they can handle, so they're perfectly capable of handling up to the 12 volts that I chose. And they also are able to handle up to 1.5 amps of current, which is twice what the motors draw. The motors draw around 600 milliamps. So even if it was like a stall current and the motors were stopped, the current would go up to possibly 1.2 amps, so still under the maximum rating for the transistors. You'll see it in the schematic, but in the data sheets it's noted that they do require diodes for voltage protection. So those were connected in parallel with each transistor. The final component are the DC gear motors that I chose. Generally in commercially available PV, like solar trackers, you'll see linear actuators used. I don't have much familiarity with those, but I am familiar with gear motors and rotational machines, thanks to Mr. Broad. So that is what I chose to work with. The motors I chose they come in at 3 RPM with 12 volts. It's like a 1 to 1800 gear ratio to allow for more torque, so it can handle more weight. I don't have the exact figures, but I believe it was something like 50 pounds per centimeter, which is a lot more weight than I needed to, so they're kind of overpowered for the purpose, like their application. So we'll look into the technical details of my project with the schematic. As you can see, I did break it up into the elevation axes and the azimuth. Again, both circuits are the same, so for the purposes of this presentation, I will just be diving into the elevation axis. Also pictured above here is the power supply coming in, which is the 12-volt DC battery going to the rocker switch, and then it just feeds the straight 12 volts with no voltage regulation. So the first part of the schematic and the logic flow is the 12 volts being fed as the power source up here, and sunlight coming as input to the 4 LDR sensors. There are 2 LDR sensors for each axis, and as I stated, as the sunlight varies, their resistance values varies. This provides differing outputs for the voltage divider here. The other components you can see are the potentiometers and 2 10K resistors that I have in series here. They're also being fed to the comparator circuit, and that's what makes up the voltage reference for the comparator circuit. So here shows the comparator circuit. As it's fed in, we have voltage reference going into the positive input for output 1 and for output 7 here. Then we have the LDR sensors with the voltage divider providing what's referred to as V in here. What the comparator does is look at the reference voltage, look at V in, and assesses which one, if it's a higher value, if V in is higher or lower than V reference, it varies the output on pin 1 here. The reason that's beneficial is because as the sunlight varies, the sensor's values will also vary, as I stated, and that will effectively change the output that we get from the channel 1. The same thing is true for the second comparator circuit in this axis. So as the sunlight changes, if the resistance values of LDR4 changes and is different from the value of LDR3, then V in here will be a different value from V reference, and again would change the output here. Okay, so between the H-bridge motor control driver, they take the signal from the comparator circuit. So as you can see here, they have R11 and R12. I changed the positions of them just to make it easier to see on this drawing, so you can see how the signals come into the H-bridge motor control. So if we have 4 transistors, and these are the protection diodes I spoke of, which are connected in parallel with the transistors, providing reverse voltage protection. So as the circuit works, it's fed with a 12-volt power source here. And as the outputs from the op-amp change, we'll call this R11 and R12. So if the output on R11 is higher than the output of R12, the current is going to want to flow down through Q8 here because the bias current would be active, and that's what triggers the transistor to operate. So if we have R11 higher than R12, we get forward rotation of the motor, or clockwise rotation if you want to call it. And so the current should flow down through Q8, which is this transistor, through the motor causing the forward rotation, and then down through Q5 to ground. If the inverse were true and R11 were lower than R12, we would expect backward rotation or counterclockwise, which you can see pictured here. So in this case, with R12 giving a high reading, it activates Q6 here instead of Q8, and the current flows down through Q6, through the motor causing counterclockwise rotation, and then out through Q7 to ground. I've also just included a truth table that helped me understand what to expect for the movements of the motors. Given that I was dealing with both axes, this was super helpful to see during troubleshooting and during the build if my circuit was actually working as I expected it to with the motors. So it just summarizes what I had previously stated with the forward, backward, and here you see stationary as an option. So if the sunlight were the same over the 2 LDR sensors, you would expect no difference in the readings from the op-amp, which delivers the same output to the H-bridge motor, resulting in a stationary motor, no movement. So although My project doesn't contain any code. I did create a flow chart just so that I know like the flow of logic and I can keep track of it for like what my expectations are. So the flow chart, obviously we have, is the sunlight directly above the panel? If yes, then there should be no movement and motors 1 and motors 2 should remain still. If the sun is directly not over the PV panel, then the azimuth sensors are checked to see if they're shaded. If they are not shaded, then motor 1 or the azimuth motor should remain stationary. If they are shaded, then you would expect motor 1 to rotate accordingly until the sensors and the panel is in its optimal position. Once that is completed, then we look at the elevation sensors, checking to see if they are shaded or not. If they are not shaded, then the motor should remain still. If they are shaded, you would expect the motor to rotate accordingly and adjust the PV panel's position to best capture the most sunlight. Next we'll look at the final build. I know it's hard to see on the ground here, so there are some pictures included so you guys can see it better. Just providing a top view and a front view of the electronic enclosure, which holds the PCB. And here's the final build of my PCB. This is before I had soldered all my connections. Once all the wiring is in there, it gets kind of complicated and difficult to see all of the components and terminal blocks clearly. So I took this picture before I had done so. Highlighted here are where the 4 LDR sensors come in. So the 2 on the left here are responsible for the elevation axes, and the 2 on the right are responsible for the azimuth. We have the 12-volt battery terminal, and then each motor. So M2 would be the elevation motor, and M1 would be the azimuth. Following the build of the printed, or during the build of the printed circuit board, or during the assembly, I had realized that some of the design wasn't what it was supposed to be, and some of the traces needed to be corrected. I had gone to my advisor, Mr. Legier, to do some quick troubleshooting to figure out the most effective and the best way to correct these issues. You can see it from here because it's on the bottom side of the PCB, but I effectively had to cut 2 traces that were incorrect and then add jumpers in place for my grounding to ensure that I had proper signal flow. During the project, I conducted 2 tests. The first of the 2 was the tracking accuracy test. Just a simple block diagram here to show you the flow for the testing. So I did the test in a simulated environment because I couldn't control the weather, and unfortunately the days I chose to test happened to be the cloudiest days. So I did it indoors with just a high intensity LED flashlight to mimic the sunlight. I measured the light with a lux meter to determine like the ambient room lux and how much the flashlight was outputting. And then I moved the LED light according to the sun path chart, which I'll show in the next slide. After moving the sunlight accordingly, I recorded the effective position of the PV panel to see if it was meeting my expectations. So the sun path chart that I used is pictured here from sunearthtools.com. If you can see the yellow line, and it's hard to see, but the yellow line is what the sun movement is in the month of May. So that was what I tried to mimic with my flashlight positioning. Essentially the test was determining if the elevation motor and the azimuth motor would react accordingly to the change in sunlight. I'm happy to say they did. Although I could have improved upon the test because it was really only testing the accuracy of the elevation motor. There wasn't much deviation in the azimuth motor because I wasn't varying the horizontal position of the light, I was just changing the arc. The second test I completed was the light intensity test. So again, I did it in a simulated environment because of weather. But I used 2 different flashlights, a high intensity light and a low intensity light, measured the light readings with the lux meter, and then recorded the status of the tracker to see if it was operating as intended or not. So this isn't the exact table I used for the test, but it's a sample of what I would use. So I took a reading of the ambient light in the room under both conditions, and then just checked if it was operating correctly or not. So after calibration for the low light, the panel was moving accordingly with the flashlight, and under the high intensity, again, after performing calibration. When I say calibration, what I mean is just adjusting the values of the two potentiometers that I have, which changes the reference voltage. After conducting the light intensity test, the motors were both operating as intended and were considered a successful test. So in conclusion, the status of the project as it stands is functioning with an asterisk. So like I said, I did run into some mechanical issues during the build, and that resulted in instability in the main shaft that's connected to the azimuth motor. Prior to my evaluation, I had it somewhat functional, and I just had the sensors left to be mounted. And during transport, I actually broke off the supporting shaft that was on the azimuth, which resulted in me having to add 2 supporting shafts just for the purpose of this demonstration today to show you guys how the motors work. Ideally, those would not be on the final build. You would just have the single shaft going to the motor. So lessons learned was patience, a lot of patience. When doing troubleshooting, it doesn't help when you get frustrated and bang your head off the wall. So if you can take a step back, reassess it, and then just keep trying iteration after iteration until you get some kind of functionality. That was also a lesson learned during the PCB. I really struggled with the PCB design, being my first time doing that, but I found it a great opportunity to learn not only KeyCAD, but what goes into actually designing a good PCB board, or PCB. In my design, there are definitely some improvements I could have made. As you saw in the picture, my terminal blocks were located around the perimeter of the board, which made my life so much more difficult when I was actually going to connect the wires. If they had just been all on one side, it would have been a lot easier to do that. And it would have cleaned up the look inside the enclosure. When you open it now, there's just wires going over the top of the PCB board, so if you were to do any kind of troubleshooting or assessing it, it's hard to do so without the wires getting in your way. Future upgrades I could make to the project would be to, I guess, weatherize it or make it more suitable to work in like Canadian climates. So like with the cold and the rain, all the components are rated to work as temperatures as low as like minus 40 degrees Celsius. So it's not the temperature itself, but the water. It's not exactly waterproof, so if you were to have it outside on a rainy day, you can expect it to stop working very quickly. So that would be something I would include in future upgrades if I were to change anything. Also listed here are just the references I used for the pictures that you saw in the presentation, and also some sites that I used while gathering research and data for my project. And that concludes my presentation. Bear with me for the demonstration. You can expect it to be unstable, unfortunately, because I did have to add those supports last minute, so I don't expect the full functionality that I would. So here's the 12-volt battery. Pictured here, you can barely see it, is the charge controller that actually came with the PV panel. So instead of buying another one, I just decided to use what came with it. Alright, so batteries in. Once I plug the load in, oh, I should also state, while I was troubleshooting this weekend, I actually disconnected the rocker switch, so that is not operational for this demonstration. So once I plug in the output to the charge controller, you'll see the panel start to move. So again, not super steady because I ran into that stability issue. But the idea is, as the sunlight is varied across the two sensors, that it would adjust the azimuth motor, which is trying to optimize its position right now. And also, there we go, and also the elevation motor, which is located, yeah, on the side here. Yeah, I wish I could have better functionality for you, but unfortunately this is the state that it's in. I guess that concludes the demonstration of it as well.
Yeah,
Schematic, please.
Schematic, sure.
Yeah.
Just the general overview.
yeah, start with the,
Okay.
Yeah.
I'll start here.
Sure.
So you had mentioned that both schematics are the same elevation and azimuth.
Yes.
I
Oh,
noticed capacitor C1 in elevation, which is not present in azimuth. Can you explain that?
yeah, thank you for mentioning that. Yeah, I should have in the presentation. That is a decoupling capacitor, which when going through the data sheet for the L2902, it was suggested to include, I believe it said a 0.1 microfarad capacitor, as close to the IC's input source as possible. Perhaps I could have positioned it better in the schematic, but that is the purpose of the.
Where it's located now, is that an input, the input power source for that IC?
No, the input power source would be up here. So the capacitor should be placed here and then going to ground as well.
Yeah.
Yeah, so I guess they're the same minus the capacitor. And also, the elevation axis also shows the supply voltage coming in and the ground, which is not shown on the azimuth.
You referred to our, actually, you have a slide that yeah, I mean, it's closer. You referred to R15, 16, et cetera, as potentiometers. Can you clarify that? Are they actually potentiometers?
They're, yeah, trim pots is what I used. So,
Yeah.
yeah,
So you purchased a 3-terminal device, right?
I did, yes.
Are all 3 terminals connected independently to the PCB?
They are. There should be a connection to ground shown here, actually.
Uh-huh.
For the 3rd pin, which I'm just realizing I'm missing. Thank you, yeah. Yeah.
Because this is misleading, isn't it?
It is, yeah, it doesn't look like a potentiometer.
It
even
doesn't look
as-
like a potentiometer here.
But a
And
very
that kind of, when you said that, like, hmm?
Sure, yeah,
Okay.
no, you would expect to see a 3rd pin here showing the 3rd terminal that's not being used, connected to ground
Okay.
here, yeah.
Yeah. So which part of the potentiometer
Mhm.
is missing from your schematic?
Which part is
Yes.
missing? Hmm,
Because we agree that there are 3 terminals, actually, not 2.
There are.
Okay, so which terminal is connected to ground?
The 3rd, so I have the
Actually, like in your, if
Physically,
we looked at
yeah.
your PCB and then
The 3rd.
reverse engineered the
Yeah.
diagram from the PCB,
Yeah,
which terminal would we connect to ground?
it's the 3rd terminal that I have connected to ground. So the center
Which
one.
is called what?
I'm not sure the terminology on them. Yeah.
Can you describe it?
Can I describe it?
Yeah,
Outside of,
because there are 3 terminals.
yeah, it's the non-varying resistor value. Like, I have the 1st pin and the middle, the 2nd pin connected to my 2 components, which is where the resistance varies.
Okay,
If you check the resistance on like the 2 outer pins,
yeah,
they're the same no matter what.
right?
So that 3rd pin
The
is what I
3rd
have.
pin.
Yeah.
Remember what we
I-
call that one?
I do not.
Okay.
No, I'm blanking completely.
Gotcha.
Yeah, unfortunately.
Yeah. Any other questions on this part? How about maybe the next slide? No, you already asked one about that one. How about the next slide after,
With
or the?
H bridge?
Yeah,
Okay.
how about that one?
Sure.
You took great attention to detail in including these diodes,
Mhm.
okay? D5 through D8 on this slide.
Mhm.
And there are actually some H-bridge motor drivers that include these diodes in as part of the package that are included internally.
Right, yes.
And you mentioned that you, I mean, obviously you had read the documentation on this this motor driver and realized that you had to use these.
I did, yeah.
Which I think is very important.
Yeah.
That you knew that you needed to put them in. What are these diodes referred to in motor control ICs?
If I'm not mistaken, it was, I want to say it was the over voltage protection.
What are they protecting against?
The reverse flow of current.
What would cause that in, when we're talking about motors here, right? So
Yep.
what would cause that, or what could cause that?
Like a stall current or.
What's that called? What's that caused by?
The,
What causes that?
Locked rotor current.
Okay, if you have a locked rotor,
Yeah.
that means that at some point the motor was rotating
Mhm.
at its rated speed,
Right.
right? And at some point, the motor is slowing down, or, and it may not necessarily be locked rotor, it may be that you powered the motor down.
Right,
okay?
that's also possible.
Okay,
Yeah.
so what occurs inside the motor? What do we call that? That these diodes would be protecting the.
Like protecting against like the rush of current. Or-
Well, yeah, there is a current that definitely
Yeah.
there's a current that occurs there. Why though? What's the source of that current? That the motor.
That the motor is strong.
Principal operation of the motor, right?
Right.
Yeah.
Yeah. Go back to last fall. Okay.
You made
Yeah.
reference to, you learned a lot in that course.
I
so-
did, yeah. And
I'm
I
hoping you remember it.
Applied quite a bit of it during the design of this project.
Okay. Yeah.
Freezing on the spot. Yeah. What current would it be protecting against?
Yeah, what's the
Yeah, the
source of
source
the
of the
current
current.
that these, right? If you're saying that these diodes are going to conduct a current, where's that current coming from?
Not the, would it not be the power supply? No.
Well, we're talking about the motor. This is driving the motor, right?
Right.
So what aspect of the motor, what property of the motor would cause this?
Is it-
Usually we're feeding current into the
Into
motor,
the
right?
motor,
But
yeah,
You're
so-
saying that the motor could actually feed current back to the circuit? Okay,
yeah.
that's definitely true. Why does the motor do that? What causes that? What aspect of the motor?
I definitely know this, and I can't.
You know this.
I know this. I know this. What aspect of the motor causes the current to go through?
What other rotating device does a motor sometimes act like?
What other rotating device does it have to be? Is it, no.
The only other one we covered in the rotating machine form.
Yeah, generator,
Right,
but,
it acts like a generator sometimes, right?
It
Actually,
does.
all the time that it's
Is
rotating.
that, yeah, that's where the,
So it acts like a generator,
Mhm.
and we have a certain terminology that we use to describe the fact that it does that.
it does that, yes,
Yeah,
we did,
remember?
yes. I can't say that I remember it, but,
Ah.
yeah.
Starts with, well, it depends on how you want to. There's actual several terms actually we could use.
Right,
It could start with a B. It could start with a C. Sometimes there's other terms we use, but
I'm not sure what you're referring to.
well, if the motor is being fed with an EMF,
Yeah,
right, and then we remove that EMF,
right,
okay, it's still rotating.
yeah. because it
What's
still
happening?
has the-
What's happening? It's rotating, but even though we've removed the source of EMF,
Yeah, it has a residual flow.
Well, there is-
Which
yeah, there is
contributes to
actually.
the current, which,
Yeah, and so it's still
Yeah.
cutting, yeah.
yeah, it's still cutting lines, which is still
Yeah.
generating a small current that.
It's
remains-
generating a voltage actually,
Right, yes.
that causes the current. That's the voltage that I want you to talk to me about,
Okay.
right?
Yeah, so, yeah, would it have to do with,
And it actually has quite a role in the way that the supply current is limited to,
Yeah.
right?
it is
As the machine is rotating at its full speed.
up to, yeah, because the full current that it pulls would be,
Yeah, the full current that it draws when it's at
When it's-
standstill is quite high, right?
it would be,
But then
yes,
as the machine rotates faster and
Current
faster,
decreases.
that supply current goes down
Yeah.
because of this voltage that is produced, that it's acting like a generator, right? What do we call that?
Reduced, yeah. I definitely know this, yeah.
It generates in counter to the to the applied voltage, right?
Yeah, the counter.
Counter EMF, right?
Yeah, yeah.
Okay, so why would there be, why would there be a need for these diodes then?
Because, well, if there's counter EMF, that would also reverse the polarity of the current, and then
Yeah.
it could go the opposite way for that it's intended to, and the diodes would provide an easy path to ground, so that
Wouldn't
it
they?
keeps it away from the transistor
Wouldn't
and
they? Yeah,
pulls it to them. Yeah.
exactly.
Yeah.
Thank you. Anybody else? Okay, want to go to another slide?
Can you bring the slide that you had your truth tape with the H bridge?
This one?
Yeah. What would happen if R1 and R2 were both equal to 1?
The motor would still be stationary, but you shouldn't have a case where they would both. I guess you could have a case where they would both
Could
be one.
happen if a
Yeah,
car
you could.
drives by and the
Sure.
sun's on the other end. What
Yeah,
would
and it shades them both at the same time. Yeah. Again, you would expect it to remain stationary. There should be no movement on that case as well. Yeah, I guess that would be the other option that's missing.
First, you mentioned that you had originally a single cable plan and you had to put in a second one.
Yep.
What was the reason for the second one? Was it a sizing issue? Was it
Sizing issue, and also, like I stated with the PCB design, I could have done better with the positioning of the terminal blocks. So where I had the original cable gland coming in was great for the position of the motors because they were on either side, but I struggled getting the LDR sensors that were located close to the cable gland entrance, so providing a separate entrance made it easier for me to route the wires around. That was why. So 2 reasons, I guess, sizing and the layout of the PCB. Yeah.
I can ask another question if you guys. Well, let's look at the schematic again then.
Sure.
Um,
Any part in particular?
Yeah, the comparators. Can you tell me, can you explain to me, IC1A?
IC1A.
Yes.
Mm-hmm.
Which component or components is your reference voltage measured across?
The reference voltage is measured across R7 and R15 going into pin 3. And then, I guess, well, for the full voltage divider comparison,
So what voltage does IC1A see at pin 3? If you were to use KVL to determine that, what voltage would you say is seen by pin 3?
The voltage drop after R7.
So what components then does pin 3 see if you go from the
Move out
node?
from pin 3?
Because when we say the voltage at pin 3,
Mm-hmm.
what is that in reference to?
Do you mean in reference to ground?
It is.
Yeah.
Very good. It is in reference to ground. So which components then is that voltage measured across?
Oh, with reference to ground, it would be across R15, R16, and R9.
Okay. Yep. And so in reference to, so what about R7? Why is R7 there?
To provide the additional, or the initial voltage drop so I could have the correct readings in there for re-reference.
So if you follow the path of R7,
Yep.
what are you actually measuring? Is it just the voltage drop across R7?
No, it would also take into account the voltage across,
If you follow that path
yeah.
from pin 3 through R7,
Mhm.
what else is in that path?
Are you speaking to the power source, the 12 volts?
Yeah.
Okay.
So you're actually measuring,
The 12
so
volts.
pin 3 actually sees the voltage across R7
Yep,
in series with
With-
the 12 volt source,
exactly.
right? Okay. That's interesting. Guess we're
End of time.
yeah.
Okay, you're good. Thank I literally broke it. Like I should have left it alone. It was working, and then I was like, I can.
We're making progress. Moving in the right direction.
We're at the end here, but yeah, pretty good. All right. So a lot of different places here. A lot of instructors today. Working. You're all on the Yeah, he was in this morning. Yeah, he came in for the first two practices. You guys are heading out here now. Yeah. Well, we really appreciate you taking time out of your busy schedule. We know how busy it is, and it means so much because you guys have been there, right? Andrew Love, the other DPs were already, but the three of them were here today, and they all know what it's like to go through this, right? Yeah, that makes a big difference. To know that there are people here. Yeah, it looks to me like the difficulties is still kind of pure here, and that's our goal. Yeah, we want them to sweat it out and be able to prove their true skills here. Certainly, if they can get through this, then they'll just fine in the workforce. Eh? Oh yeah, yeah. So anyway, I just wanted to say thanks for inviting me, and certainly next year, this will be happening again. We appreciate another invite. Yes.
I gotta go through my list because I'm the one that sends out and I'm bounces left and right, so I gotta stop waiting till the last minute first of all before I go through the list, but just call through, so you might get an email of are you still interested in seeing? That's actually the first time this year that 2 people respond saying that, well, I'm no longer in a position to, directly work doing, so I'd like to be removed from the list. Really? I kind of answered, oh, I'll take your name off if you give me another name. And,
Did you get a lot of people coming?
a lot of them are doing this read on there.
Oh, yeah, yeah. Yeah, we got it online.
No, it's-
No, I wasn't able to attend in person yesterday, and it wasn't as fun asking questions, because they had to do it through a text, and then you would ask them for me.
I
Yeah.
wasn't really, he put the answer out, because I wasn't really sure what he was asking for.
Well, that's the other thing too, it's like, how much of this typed message is he actually understanding, to actually feel comfortable asking the question? Yeah.
He's talking about the grants for PLC upper course.
Yeah, the commenter, yeah. He didn't. Yeah, yeah, no, the current will just flow to outer space. And, yeah, yeah. That's right. It's a virtual ground, that's all. Virtual, yeah. I didn't see any offense in this circuit. Yeah.
Just try to keep going.
Okay, it's great to see you guys. Yeah, thank you very much. And don't be shy to reach out to us if you ask us.
Yeah,
Yes, yes. We would rather take the time to go through that with you than you make a choice that you regret because you thought you knew something and you didn't.
Yeah.
So
we also got Jonathan, Thierry.
yeah, Alvarez. Yeah. Yes, he told me that back in the fall, and so we've been making some adjustments for him so that he can get to work and so on, which I think my perspective on that was he's already doing what we hope people will do after graduation. So it's like, why are we holding back from that? Yeah, so no, I was very encouraged to hear that he's working already. That's right. Yes, I don't know if you got a chance to watch his, but it's online. His presentation went very well. Yeah,
Great job on the fab of that panel there.
yeah, no, he did a great job. Yeah, yeah, it was really good. Yeah, he's gonna do well. Yeah, so.
His model was
He took some of that. He took some of that, at least the idea for it, from a pre-existing model that a student in civil built. Oh yeah.
He shows up to work and he's asking to do modeling and
Take care. Okay? Good man, checking to see if you're in field of view, huh?
Is it working? Someone said that the Wi-Fi was not
Yeah,
working.
it's, the Wi-Fi is not,
What do you
not
mean?
working. The Wi-Fi is not working.
What do you mean Wi-Fi? This is plugged in.
Oh,
yeah.
So it's
Mr. Philho had used the Wi-Fi, I think, on that computer to show functionality of his device, if I'm not mistaken. So the Wi-Fi itself is not being used to connect to the internet, it's plugged in, so it should be fine. So it should be fine. I've been following it this morning, so looks like it is up to date here. With, is it Sketch?
yeah.
Yeah, see, you can see you guys walking in front. Yeah. There's a slight delay. Extreme delay. But it seems to be working.
Oh,
Seems to be.
I had it down in classes. Yeah. I know, I wanted to see. I removed it from all.
You know what?
When did you do your crap?
really wanted to do.
That was your presentation.
How are you
Well, that's weird. It's saying,
No, it's bouncing, it's flopping.
yeah, it is. It's doing not connected.
Marvelous.
Okay, turn Wi-Fi off. Turn Wi-Fi on.
I even remember it. The new policy. You're not allowed to stay online for more than 5
I
seconds.
said, I was doing good. Okay, well, here, let's try this. Power off.
I'm trying to. I don't do it. Speaking like a
Well, you're there for it. You don't sound it.
There for closure.
That's so like my phone is there. This has one.
Yeah, that's
Oh, it's the last day. It was 23rd.
I saw.
I know.
Okay. Three morning ones, you mean?
Well, I saw,
Oh, you were here for that?
Somebody.
I screwed up your book, buddy. See? Starting at I just put the last page, you didn't look at the name. So that's I put a note on it. And then that's been and then I'll put another note there. And then this one back.
Yes, please. We're done the course. But no, I mean, I've gone through most.
I had to tell him.
Most of the presentations I've got.
So just.
Sweet.
It's time here. It's almost time. Nobody else read this read. Okay, so our last presenter of the morning is Claudio Ito, and he will be presenting his smart cane for the blind.
Yeah, thank you.
Okay.
Good morning, dear instructors. Good morning, dear classmates. My name is Claudio Ito. I'm a student at Electronic Engineering Technology program, okay, in a path for industrial controls. And today I'm introducing my project, which is a smart cane for the blind. I'm grateful for my adverse times, for for orienting me during this process, as well Mr. Selah at the beginning, Mr. Dr. Kodei for about my report, and Mr. Leger about my DCD. Okay, so just about my summary today, and I will do my introduction, functional review, technical review, testing and results, my conclusions, and my reference. Okay, so just let me tell you why I choose this project. Okay, so since the beginning, my intention was to build an electronic device that could help people that have some disability. Okay, so that's why I tried this, and I discussed with my wife which device could be. She remembered me about my uncle that became blind due to diabetes. So, and I did some research about this problem, and I discovered some information regarding this issue. So, according to the World Health Organization, which is ONU agency, 2 billion and 200 million worldwide has some kind of level of vision problem. But especially 253 million have moderate and severe levels. So, but unfortunately, this number will increase up to 30% by 2030. Okay, so what was the main reason for it? Well, first of all, people are getting old. Unfortunately, it's the life, and the modern lifestyle. Okay, so modern lifestyle, which is using a lot of smartphones, tablets, and so on. So it can produce some problems at the future, as well as the food. In case of my uncle, he became a diabetic, so too many sugar on the foods. So we need to be careful about this. But it's not you will not only born with the problem, so you can have it due to your lifestyle. Okay, so what usually the devices that people with some kind of blind use? Trained dogs and white canes. White canes, I draw this example. Okay, and so I tried to I built this device, and the more simple as possible, and as less expensive as possible. Because for people that don't have too much money to buy, and they can bought it. For example, this prototype, the total cost was almost $94, and I know the price can drop because this part I use the same disc, so I can do 4 handle parts. So I know that the price can be lesser. So it's good. And what I put inside my cane? I am using two types of sensors and 2 types of alerts. One of them is the red one, that is a vibration motor. That is like it's the same as the video game joystick. The people that it's vibrate, and I put inside here, okay. And the puzzle I'm using is in the blue arrow, and it's shown here, okay. The other component that I'm using is the PCB, okay. I put my PCB inside the pipe. Okay, I use a hexaw to make some baffs in the internal side of the pipe to sustain my PCB. Okay, and I could put inside. The other component I'm using is a ultrasonic sensor. It's the same that we use on our lab. Okay, I put in the middle, here in front of the cane. I put here because I'm using a battery compartment, and I could access to the ultrasonic in case of any problem. As well, I'm using as well a water sensor. I put it in the below part of my cane. It's for detecting water in the floor. And yeah, is the compartment of my battery. Okay, so talk about briefly about my. Oops. I'll talk about my block diagram. So, I will explain 3 main sections of my block diagram. The one is about my power sector. I'm using a 9-volt battery, a regular one that we can buy in stores. I'm using a glass fuse, a simple switch, manual on-off, and I'm using a volt regulation to give me positive 5 volts. Another main function is about the detection object stack. I'm using the ultrasonic sensor. I'm using the 80 mega 368. I'm using MOSFET as a gate drive, and I'm using a verbate motor. Okay. And the other main sector is the water detection, which is I'm using a plate that I saw you. I'm using a BDT in 8 mega and my buzzer. Okay. Here is my overview about my problem that I'm using. Okay, I starting my cane by beep twice times to show that it's starting mode. Okay, and I do a loop, and the first thing is she check if there's a water, and if no, or if yes, a beep, and if no, it scan about if there's an objective in front of you. If yes, it calculated the distance. Okay, if the distance is less or equal or less 50 centimeters, it vibrates more intensity, and if it between 150 and 50, it vibrates less. Just to indicate if you are approximate, it vibrates a little, and if you are close, much more. Okay. So, so just about the function. The main sensors is the ultrasonic sensor in water in front of the cane, and I have a turn on and turn off switch on the handle part. Now I'm introducing about my schematic. I will explain just this part, because the other parts I will explain separate. Just I'm using the ECSP, that is a in-circuit serial programming model to upload my program that I use in C language. I'm using the MPLAB IDE. So I use this model to upload my program. Okay. now I will explain separate this. So, about my power sector, I'm using a battery, 9 volts. I'm using a glass fuse of 500 milliamps. And I calculate this, I calculate by summing my regular consumption about my components. In a regular mode, it's only 100 milliamps, but in case of, especially because the vibration mode, it requires more amperes, so it requires almost 260 milliamps at starting if it has a load in the vibration mode. So I decided to choose a 500 milliamp, and my voltage regulator has output as 500 milliamps. So I decided to choose a 500 milliamps, and I have a manual on-off switch. I'm using a voltage regulator, 2 capacitors, and a diode here. And the diode here is about, in case of any problem about my voltage regulator, and has a high voltage output, and it allows a path to volts that don't damage the rest of my circuit. Okay, and I will get my 5 volts to feed all my circuits. Now I'm describing about my ultrasonic sensor. As maybe the ultrasonic sensor has 2 lanes. One of them is for transmit, and the other is for receive the waves. Okay, so how I use it? So, in my program, I use 2 digital pins, and I send a command to the ultrasonic sensor. I send a pulse of 10 microamps and it make the ultrasonic release 8 waves to detect the obstacle at 40 kilohertz. And in case of any obstacles occurs in front of the ultrasonic chip, the waves will return to the ultrasonic sensor, and it will be detected by the lens, receiver lens of the ultrasonic sensor, which is this air. So as soon as it's received, it sends to my PD, my pin, digital pin in my program, and it calculates the distance. So how it does? The first wave that it receives, the program starts counting, and as soon as he receives the last one, he calculates how the width and divided this value. In case of centimeter, is by 58, and you get the distance in centimeter. Okay, that's how it works. So the next part is about the water detections, and I'm using NPN BDT because NPN has more carry. The charge carry is more electrons, so I can use just a little if I have just a little amount of electrons, I can activate it and turn it in saturation mode. Okay, so how it works? I have my sensor plate. It's in parallel. The trace is in parallel, not contacting. So, and it receives a 5 volts voltage. As soon as the water is in contact with the water sense, it creates a conductive, and goes to I use a potentiometer. The potentiometer is here just to to have a way to calibrate the sensitivity of the water sensor. Okay, that's why it's here. As soon as I set the potential, it allows some amount of voltage to base of the BDT. So the BDT, as soon as it receives for the threshold of this BDT is 0.7 volts. As soon as it receives 0.7 volts, the base emitter junction is established and allows some current coming from base to emitter. And according, if I have amount of level, it creates a pathway to draw, to allow the huge amount of electrons to go ground. And what it makes the voltage drops to almost zero. And it is the way that I can detect the water, because I'm just checking if it is high level or low level. So that's the way why I'm using BDT here in this case. Okay, this is it's about the buzzer. It's a simple, it's a 5 volt buzzer. It has 85 dB. So I just put my digital pin PCB in high level, and it gives 5 volts to buzzer to work. Okay. So here is about how I turn on my vibration motor. Okay, I'm using a MOSFET here in channel MOSFET, because it is used to be a quickly switch, and in channel needs a positive voltage. As soon as I'm using 80 mega, it's give 5 positive. That's why I'm using N channel, not P channel. And here I'm using a voltage divider to prevent any huge voltage can benefit the MOSFET. And this resistor, it works as a pull-down resistor, because MOSFET has some capacitance inside him. So using a pull-down resistor, after it uses it forces it to be off, always off, or in case when we start the device. That's why I'm using this resistor, and I'm using my vibration motor, and I'm using another diode here, and it's a freewheel diode that, as mentioned before, it gives some path for the residue of the current that the motor can produce after it turn off, and it gives another buffer to not damage my MOSFET here. Okay, so I'm talking about my testing result. So as mentioned before, it works in a simple way. So I just in our lab, in our previous labs, I could detect a large object as I pretend, but in my test I try to detect a small object on the floor, because nowadays we have a lot of pads and babes. So my intention here is to check if I can detect a small object, and the other way, another test was check how the minimum level of water I need to work about the what that can molhar, wet, that can wet the person. Okay, so it's a simple, just, I have two range of distance. This is the closer one, and this is the medium. Okay, in it among 51 to 150 centimeters. So I use 4 types, 4 high of box, and I could note that it cannot detect a small object when I'm close to them. Okay, so that's one of my conclusion in advance. And the other test was regarding about the minimum water level. Okay, so how much high is the water plate? I can move it to up or down. Okay, but the intention of it for just to know that the minimum height of water, it will advise the user about it. So in 5 millimeters, so it will do a beep to alarm the user about the wet. Okay, so my conclusion is I as predicted at the beginning, it can detect large objects, and he can advise the user about the water in the floor. But the negative what I discovered is it cannot detect small objects on the floor. So it needs to be improved. I need to put another sensor in the below part to detect it. And I wish to put some Bluetooth components to, for example, if the people lost where the blind is, and it can start a beep start it to beep and indicate the person, or maybe he can go this way or this way. That's some of the other people with the blind to help him about this. That's what I think about the improvement for this. Okay. So this is my reference. Thank you. I put some level of water just to show how the water detection works. Okay. So as mentioned before, starting it will beep twice. So it indicates that it is working. So just everybody could see?
Yeah.
Okay. Just okay. So try to just a minute. I forgot to set up my bar. Okay. This is the minimum distance I choose 50 centimeters, and this is to complete one more 100 centimeters. So in total is 150 centimeters. So I would like to ask Daniela to be my assistant.
Can you turn the camera so?
Oh yeah. This. My daughter tried to help me. Got some way to show the vibration. It's not easy to show because it's not so strong. The people that handle it can notice this. So I hope it can be noted. So. So as soon as I detect here, I don't know if you can see, there's a little vibration here. And as soon as I turn a bit closer, it vibrates more intense. But unfortunately, I didn't get a way to show, but it's, believe me, vibrate more intense. So, thank you. Yeah. So, now I'll try to. This vibrating, but as soon as I do, it cannot detect anymore. So this is why it's necessary to put another ultrasonic sensor here. So, but it will be for the next future project. So that's it, Mike.
Bring up the schematic plug. Yes, enlarge it, please. What does the acronym ICSP stand for?
ICSP, in control, in circuit programming model, and this is a method to communicate with 80 mega, and I'm using a PKIT device, and it uses some lines as a MISO, SCK,
Right.
Mosing.
No, it's just the acronym ICSP. You didn't say what the S is.
The, excuse me, the F.
The letter S.
S. Encontro, encontro serial programming.
Okay. Thank you.
So,
You guys have any questions?
Can you explain to me your water sensor, how that works to detect?
Okay.
How does it work to detect? No, the water sensor.
Oh, the water
And I'd like you to do it from
Okay.
the,
Oh,
from
okay,
these,
Water
schematic.
Water
Yeah,
sensor.
there you go.
Okay. Here, I'm using this plate that has traces in parallel, and it is connected for 5 volts. So, as water has some level of conductivity, as soon as the water in contact with this plate, this water sense, the voltage goes to
The what goes?
the current goes to here, to my potential, that I can control the sensitivity, my plate, because before produce this, I didn't know how level of sensitivity it could be, so a potential as indicate for me to use it. It helps to control the sensitivity, because without it, it could be always alert every time. So if I couldn't detect the water, it will continue beeping. So this potentiometer allows me to control the sensitivity. So
Okay, so what's formed between your sensor and R4? What is formed there? What's the basic circuit?
it's a potentiometer.
No, but R4 is a potentiometer,
R4,
but the
yeah.
circuit between the water sensor and R4, what basic electrical circuit is it forming?
Between this and this.
Yes, what basic circuit is that? What basic first gear circuit?
Short.
No, there's no short there.
Okay.
You have a 5-volt voltage source, you have a water sensor, and you have R4. What is the basic fundamental circuit that's forming? Replace your water sensor with a resistor.
Okay.
What basic circuit is that? Two resistors in series across a voltage source. What kind of circuit is that? Is it a current divider?
In series?
In series.
No, in series no.
Oh, so it's what? It's not a current divider, what is it? How does it trigger? How does it trigger? When you put water out in the water center, how does it trigger Q1?
By conductivity.
Okay, so that becomes conductive, so it becomes a form of a resistor. So how does it trigger Q1?
Oh, okay. Is the current the DDT that I'm using is a current oriented device.
All
I'm using
all NPN transistors,
okay.
BJTs are, yes.
Okay, so I'm using I'm applying some amount of voltage.
Okay,
It's a
so,
mechanism.
so you're applying a voltage there. How much? What dictates the
It
amount of
depends on what, I don't know exactly the value,
No,
but,
okay.
but it needs to be more than 0.7.
Well, it has to be 0.7, it can't be more.
Yeah, it can be more, but at least it's 0.7.
No, it has to be 0.7, it cannot be more.
Okay.
It cannot be more. The base emitter junction, or yes, the base emitter junction cannot be more than roughly 0.7, 0.6, 0.7. So, but how does it work that you apply 0.7 volts then?
By regulating. the
No, you don't. When you were using it, you weren't turning the potentiometer.
Yeah. Yeah, before I put inside, I did some tests.
Yeah, okay, so, but then when it's done, and you have your cane outside the water,
Okay.
it's not ringing,
Yes.
and when you put it in the water, it rings.
Okay.
So what changes for that voltage to be applied there? You can imagine your water sensor being a
Yeah,
resistor. Imagine it being a resistor.
Okay, as soon as we remove it from the water, there's no more voltage going to.
The voltage doesn't go anywhere, so it doesn't matter.
Current goes to.
But it's not the current that's changing there. Your water sensor makes what change? Your water sensor is a resistor in series with another resistor across a voltage supply. What type of circuit is that? What basic type of circuit is that? It's not a current divider. What else could get divided? If you're not dividing current, what else could you divide?
We use it as a series resistor.
Two series resistors across a power supply
Yeah.
with a tap is what kind of circuit? Is it a current divider?
No, it's not.
It's a something divider. Starts with a V. Starts with a V. Ends with voltage. It's a voltage divider, right? So it's a voltage divider, trust me?
Yeah, just.
Okay. So what's the varying part of your voltage divider? What part varies in your voltage divider?
The current.
No, which resistor varies?
No, in this case, it's potential.
No, you've set that, you've not touched it. When you're operating, you're not touching it. So which part varies? There's only one part left.
Yeah.
There you go, it varies. Its resistance varies
Yes.
from open,
Yes. In
To-
this case, it is open.
from
without
open
the
to
water.
another value, right? Therefore, when it's open, the voltage is all across the resistor, the water sensor, not R4 has 0 volts, okay? And when it's conducting to some amount, there's some across the water sensor and then some across R4. At that point, keep going, keep the story going,
Okay, yeah.
keep going.
Goes to my base.
Okay, so how much voltage across there?
Should be at least, should be 0.7
Yeah.
volts. So it turns this junction in forward bias.
Yeah,
Okay, so it allows some electrons to go from base to here.
well, that's not really true if you're talking electrons.
Okay.
If you're gonna talk current, I'll go over
Current,
that.
okay, current, yeah.
If you're talking electrons, it's going the other way, right?
Current, okay.
Okay.
And it, what I read it told me as if I have some, okay, it's made for.
If you're forward biased, yeah.
If the amount of current in the base is more than the IB, the minimum, it set this current, it allows the the collector to emitter, allows the currents goes through this.
How much current flows there?
Almost everything.
Almost everything, okay.
Yeah,
But how
possible,
much?
definitely.
How much?
Here,
How much current could flow there? If you have a current IB, how much would you expect IC or IE to be, or IC, doesn't matter, IC? How much would you expect IC to be? If you have a current IB,
I see could be, can I use a calculator? You want to?
well, there's no numbers. There's no
You want
numbers.
to
If
know-
IB, if you have a current called IB,
Okay,
how much would you expect IC to be? How many times bigger would IC?
Something IB.
Yeah.
the IC
Roughly, approximately. There's a factor there.
because in VDT I have the gain of the train.
Yeah, what's the gain called? The current gain, that's right.
Yeah.
What's it called? You're right.
I don't remember how much is the train, but
Is it alpha?
that.
Beta, there you go, it's beta.
Yeah.
So IC will be beta times IB,
Yeah.
right? Okay, so you'll have IC current going through, okay? And if it's switched, if it's fully saturated, what will be VBE? Or VCE, sorry, maybe mistake.
Yeah, VCE, so it will drop the voltage.
Well, how much will VCE be?
VCE
Yeah, how much will it be?
after saturated,
Let's say it saturates, yeah, it would
Yeah,
saturate.
okay. It goes to almost, I saw it's a 0.2 volts.
Okay,
It will drop.
sure, for a VC5, yeah, I believe that. 0.2 volts, so that means how much is gonna be applied to pin 23 then? If it's 0.2 volts.
So I think in the code I use
No, we're not talking about code here. If VCE is 0.2 volts, how much voltage will be applied at the point, at pin 23?
Okay, I'm comparing with 0 because I'm
No,
looking as a
it's
low.
not gonna be 0, you just gave me that, you said that CE would be 0.2 volts,
0.2
so I'm asking you, what would it be at pin 23?
0 in my programming, it indicates that.
I don't care what you're programming, I wanna know if you put a meter there, what will you see?
0 here.
You'll see 0 there? You're sure not? Look at that circuit, take a look. Okay, so there,
Not 0,
VCE,
it will be 0.2 volts.
there you go, it'll be 0.2.
Almost, yeah.
Well, almost, but
Yeah,
not
yeah,
quite,
yeah,
so it'll be
yeah.
0.2 volts.
Yeah, 0.2
So
volts.
now what happens in your MCU? In your
Yeah,
program?
in my program, I use a float variable, but I think in this case,
You use
the
the
best
float.
one should be int.
You use the float variable?
I guess.
No wonder you had problems with triggering, false triggering.
Yeah,
Why would you do a float?
in the lab we use a float and.
No, you didn't, not for that,
Yeah.
not for an ADC. An ADC puts out what kind of variable, what kind of number?
0 or 1.
An ADC?
Yeah.
Analog to digital converter. Are you using it as a digital input instead?
I said because it could be digital or analog.
So
I don't know what I learned. I read it could be just could be analog or digital.
Okay, so which is it? Which is it?
For me, it's digital.
Oh, so it shouldn't put ADC then. It should be P, I don't know what the bit is, PB, whatever, PB0, let's call it PB. That should be PB0, not ADC0. But PB0 puts out what kind of number format? Float? Does it put up float? Is 0, 1 float?
If it is set for digital, it should be 0.
If it's 0 or 1, what kind of number format is that? What kind of variable would you have to use?
Int or logical?
So why did you use float?
I'm wrong. I'm wrong.
Alright.
I'm wrong.
Alright. One last thing. I noticed you have J3, P5. J3 and P5. Why is connector J3 connected into plug P5? Why shouldn't it be J5, P5? That's very confusing.
It's an external.
No, I understand why you're using a connector, but why would you call the connector J3 and the plug P5? You use different numbers. That would be very confusing. It should be well, there should be a turnaround, yes, but it should be J5, P5 or J3, P3. Should it not? And you did that again elsewhere too, I noticed.
Yeah, I didn't know.
Okay, that should have been updated, okay?
Okay.
All right, thank you.
Okay, I'm confirming that the following people are absent. Louis, Bonifacio. Oh, there you are. Bring it in front of my nose. I am, oh, you're camouflaged. Yeah, you're all here. Armpit. Armpit's in that. Jake.
Sorry I missed your presentation. I'm out of class at 8:30. It's online.
No, it's not.
I heard great things about it.
Yeah.
Good afternoon, everyone. This is the first presentation of the afternoon, and it's temperature and humidity control done by Arvid. Go ahead.
Thank you, Mr. Siddharth. Good afternoon, everyone. My name is Arpit Joshi. I'm from Electronics Engineering Technology Industrial Pathway. My project is temperature and humidity controller, and my project advisor is Mr. Siddharth. So, what is temperature and humidity controller? So, as the name suggests, it monitors temperatures and humidity in a closed environment and drives output load like a heating source and a humidifier source according to the set point requirement from the user. It has various applications like in agriculture to maintain certain point of temperature and humidity. In environment, also in data centers, in pharmaceutical industries, in industrial environment, it has like many applications where it can be used. So this is the overview of my presentation. I'll walk you through the brief introduction of my project. I'll explain my block diagram in details. I'll talk about concept drawing overview, schematic explanation. I'll talk a little bit about how I designed my PCB and how my PCB looks like. I'll also talk about something about enclosure verification. I'll give you some of the details about the firmware I have used. Discuss about test results, learning outcomes, challenges I have faced during this project, and after that I will conclude my presentation. So why I chose this project? So as I said, it has like many applications where this kind of project can be used with a little bit of changes. Also, I wanted to show my skills regarding circuit design, PCB design, firmware development, component selection, and also I thought this type of project, which includes PCB design, firmware development, can be chosen for my requirement. So that's why I decided to go with this type of project. So in my project, I have used a combined temperature and humidity sensor, which senses temperature and humidity in real time, provides that data to the microcontroller, and controller operates the humidity and heating loads accordingly. So that way it can be able to maintain stable temperature and humidity in specific area. In my project, user can manually select set points through the 4-button keypad, like increasing, decreasing temperature set points, increasing and decreasing humidity set points. Also, the main components of my project is DHT22. As I said, it's combined temperature and humidity sensor. I have used Atmega 328P. I'm using 16:2 LCD with I2C interface, 4-button keypad for set point inputs, and 2 N-channel MOSFETs to drive external loads. For this project, I have used the student version of Altium. So in Altium, I have designed schematic PCB, and I also did mechanical verification, which I will talk about a little bit later. For firmware development, I have used MPLAB IDE with XE8 compiler. So this is my block diagram. I'm using a wall adapter to provide 18-volt input to the system. So 120 volt AC input is provided to the adapter, and output of 18 volt adapter is going into 5 volt and 12 volt regulators. These are linear regulators. This temperature and humidity sensor senses temperature and humidity in in a specific environment. In my case, this is the box from where it is sensing the temperature and humidity. The sensor is sending that data through one-line interface to the microcontroller. Microcontroller displays that data to the LCD display through I2C interface. I'm using 4-button keypad to input temperature set points, so user can select increase or decrease the temperature and humidity set points according to requirement. There is also over temperature indication in my project. So this feature was added as a part of risk assessment. So if temperature goes above certain limit, this can indicate, in my case it's a buzzer, so buzzer can indicate that the temperature is over certain limit, so the system needs to stop. For driving external loads, at initial phase I was going to use L293D, which is edge bridge driver, to drive my DC motor, but then I realized that instead of using that IC, I can do that work with the MOSFET. So I'm using MOSFET to drive my external fan. Also, there is a heating source. So I'm using light bulb as a heating source. So I'm using a relay to operate that heating source whenever required. And I also have a humidifier inside this box, so controller can control humidity whenever needed. This is my concept drawing. So as you can see, this is the external box. I'm using 2 enclosures. So this is my external box and this is my main project. So in external box, I have a humidifier, fan and light bulb, which I'm using as a heating source. On my main project, you can see that LCD is there to display temperature and humidity. It also displays temperature set points when we change the temperature set points to the keypad. Through the keypad, there is a temperature plus minus, humidity plus minus, so you can increase or decrease the required set points. The wall adapter is providing 18 volt 1.1 ampere input to my project, to the regulators, and through regulators it can power my DC fan and other components like microcontrollers as well. And if like this is my sensor DST22. It senses the environment over here, like temperature and humidity from here, gives data to the microcontroller, and microcontroller drives the heating and humidifier source and fan according to the requirement, like to control temperature and humidity. This is overview of my schematic. As you can see, I have voltage regulators, programming connectors, switch control, LCD connector, microcontroller and IOs over here. I will discuss it about in next slides. So this is my power supply. 18 volt input is coming from here, from the DC jack. This is for 5 volt regulation, and this is for 5 volt regulation. It is linear regulators. This capacitor is for line regulations, and this capacitor is to improve transient response whenever needed. So this is my ICSP connector, and this is my keypad connector. ICSP connector has MISO, MOSI, and SCK signals, which is basically SPI protocol. And this is my keypad over here. I'm using internal pull-up resistors for my keypad, and my keypad looks like this. For internal, like initially I was having issues with the debounce control. So like it's like when I was trying to press a single button, it is detecting multiple button presses, so that's why I have decided to control debounce in my software. This is my LCD connector and this is how I interface my LED. So it works on 5 volt. LED plus and minus is for LED backlight, LCD backlight, and I'm using I2C interface, so serial data and serial clock is there to provide interfacing with the microcontroller. As you can see, I'm using a fixed value resistor because previously in prototyping I was using a potentiometer. I measured the value of potentiometer, it was around like 480 ohms or something. And then after prototyping I decided to use fixed value resistor because I was not going to change that value afterwards. This is my I/O part 1. So as you can see, this is my keypad connections. This 4.7 case R pull-up resistor required for I2C interface with LCD. This is a typo actually. It should be 51K, 52K is not a standard value. So I'm using 51K value for the pull-up of reset pin. Also, this is the BSP22. It works on single wire interface, which provides data of temperature and humidity, real-time temperature and humidity to the controller through the data pin. Also, this is piezoelectric buzzer I'm using for over temperature indication. So whenever the temperature is higher than certain limit, it will indicate that there is you need to control the temperature. So this is my I/O section part 2. As you can see, I have provided TPs like on almost every pin. This is to ensure that I should be able to debug my hardware easily. So this is something, there is a concept called DFT, design for testability. So I have added TP for that, so that if I want to debug my hardware, if I want to check my connections in PCB, I can easily do that because it's not always easy to probe on pins and check the voltage level. So that's why I have provided TPs even on NC pins which are not connected. MOSI MISO IC case for ICSP connector. As you can see, I have used external crystal. This is 16 megahertz crystal and with the load capacitors. On PD0, I have my humidifier driver. So whenever my box humidity is less than set humidity, it will turn on the humidifier and the humidity will increase in an environment. Same as this is for DC fan. So if my box temperature is greater than the set point, it will turn off the heater and turn on the fan. And in this case, I'm using 12 volt DC fan. I'm using a relay to drive external heat source, which is a light bulb. So relay has external connection of 120 volt AC and external light bulb. So this connection is going to the light bulb. So whenever the box temperature is less than the required temperature, it will turn on the heating source and bulb will turn on it, and it will try to increase temperature value inside an environment. So this was my schematic. This is my PCB design. It's a 2-layer PCB. I have outsourced my PCB to PCB Bay. In my PCB, they have used FR4 material, and as you can see, this is my sensor connection. This red color is my front copper, and the blue color is my bottom copper. This is my sensor input. I have also turned on a top overlay so that we can see the components on the PCB. These are my voltage regulators, and these are my capacitors for voltage regulators. I have used 1206 SMT components for capacitors and resistors, basically for passive components. This is my Atomega 328P. This is my keypad connections, and this is my LCD connector, and I2C connection is going from here to the LCD connector. This is my driver section, load driver section, and loads are getting connected to the terminal blocks over here. As you can see, I don't have any ground copper over here. I have provided ground copper in both front and back. So I don't have ground copper here because this is AC section, and it is we need to provide proper creepage and clearance between AC section and DC section. Otherwise, it can get arced to the DC voltages. So that I have provided proper clearance and creepage between AC and DC sections. I have also used stitching wires to improve heat dissipation and ground connectivity. Yeah, so for enclosure, I have taken stepwise from the manufacturer called Serpec, and for the components, I downloaded stepwise from the manufacturer's website. So basically, enclosure verification is something that you can do to check if your PCB is fitting into your enclosure properly. And there are another benefits as well, like if you want to see your footprints are correct or not, so you can import step models of the components inside of your PCB, and you can check the mechanical compatibility between PCB, your enclosure, and other peripheral components. If your components are touching the enclosure insides, you can shift your components and check, and you can save from rework after you get your PCB. So yeah, basically there is a feature in Moncton you can do this, so I have done that too. For firmware, there are a couple of functions I have used in my firmwares, like as I said, button debouncing. I am providing 100 millisecond delay for button debouncing. Sensor integration is kind of issue I was facing when I was developing a firmware, because like it works on single wire interface, and initially I didn't know that it needs 16 megahertz crystal, 16 megahertz clock to work properly. So after initially I was using manual functions. I have made some functions to initialize that sensor, but it was not working. So directly I used DST22 header file provided by Adafruit, which is manufacturer of that sensor. So I'm using that header file for sensor integration. For LCD management, using I2C protocol. So this is the control logic over here. So if box temperature is greater than temperature set point, the fan, it will turn on the fan and turn off the heater. If box temperature is less than temperature set point, it will turn off the fan, turn on the heater. So same control logic is followed for the humidity control as well. And this is for button sensing. So if button state, it detects the button state and compare it with the last button state, provides debouncing delay, and senses if there is logic low on the button. And if there is logic low, it will increase the humidity. It will display data over LCD and provide 700 millisecond of delay for LCD display. So same thing is followed for temperature plus minus as well. So I did some testing as well for half an hour. I have some test data as well, and result of test data is displayed over here. And basically I have used thermocouple to place inside my box and took it as a reference and measured the value from my DST sensor. So the system is controlling the temperature with plus minus 0.5 degrees Celsius. Same for, I have used a mini humidity meter and I placed inside the box, and I can say that humidity is getting controlled with plus or minus 2% of tolerance. For keypad functionality, keypad is working fine now, and it's basically getting data from the user for temperature plus and minus, and to change the set point values. Now, before I discuss about my learning outcomes, I would also like to discuss about some limitations of this project. As you can see, this is not a closed environment. I have vents in here and on this side as well. Because of that, it cannot go below, the temperature cannot go below the room temperature, and humidity cannot go below the room humidity. It can increase, but it cannot go below the room conditions. So that's kind of limitations of this. And also, after some testing, I noticed that my PCB is heating up. So I need to ensure proper thermal management inside my PCB and product, or maybe I can use external heatsink or something. So yeah, so that's kind of limitations. For learning outcomes, I learned about circuit design, PCB design through this project, like how to properly put clearance between AC and DC voltages. I got some good knowledge about component selection as well, also for budgeting. I had some issues with due to dry solder. I was not getting some signals after I received my PCB, so I spent some time for hardware debugging as well. Software debugging as well. As I said, I had some issues with debouncing and sensor integration, so I dealt with that issues as well through the software debugging. I was able to meet the project deadlines and manage the project efficiently. So these are my learning outcomes. For conclusion, I would like to discuss about the cost of the project. So the estimated cost of the project was around $200, but the actual cost is close to $140. I overestimated cost for my second enclosure, and also I haven't paid any manufacturing fees for my PCB. I just paid for import duties and shipping fees. So that was about my cost estimation. For future, I would like to analyze FMECA, which is failure mode effect and criticality analysis for my project, to make it more robust. Also, I said about heating issues. So I would like to remove those issues as well by using external heatsink, providing proper thermal conductivity in the copper area or copper usage. And I would like to implement PID control in my firmware, which will make my process more gradual and more efficient. So to conclude, I can say that project is working fine. Of course, it has some limitation, but it's working fine, and it's inside this box it's controlling temperature and humidity properly. These are my references from the fruit and syrup pack, and that was my presentation. Thank you all. So I'll do the demo now. So this is my main project, and this is my external box. So basically it will start on room temperature. As you can see, the room temperature is 21 degrees and room humidity is 42%. So through this I can increase or decrease the set point. So the temperature set point is right now 27 degrees. So as you can see, the light bulb is on to increase the temperature according to the set point, and humidity is 61% and my set humidity is 61%. So the humidifier, which is a white thing over here, is off, and the fan is running on low RPM to access any extra humidity outside. So 56% is humidity right now, so the humidifier is on because our set humidity is 61%. And if humidity goes above 61%, the fan will run on low RPM and decrease humidity below 60, below 61. And if it goes below 60, humidifier will turn on. And same thing is happening for heating source as well. Our set temperature value is 26 and the current temperature right now is 23, so the heating is turned on, and after a while the temperature will increase. We might need to wait for temperature to increase. So I'm open for any questions if you want to ask. As you can see, the temperature is increasing. It's 24 now.
When you press the temperature, the humidity set the points.
Yeah.
How do you know which point you're setting to? Does it display on the screen?
Yeah. So that's one more thing I would like to add into the project, because if I press this button over here, it will increase from the current value, and if I press this, it will.
How do you know how far it increases?
No, it only detects only one push.
No.
So it only increments by one point.
What's the feedback mechanism that's your question?
Yeah,
How does the user know?
If I hit it 3 times, I go, oh, I don't know if I hit it 3 times or 4 or 5. How do I know where I'm at?
Yeah, so I have provided like 700 millisecond of delay in between.
Yeah, no.
Yeah, but how do we know what temperature it's set to?
Can you see your set point on the screen, on the LCD screen?
Oh. Okay, we just didn't
You
see
can
that.
see
That's
it.
what- okay, yeah.
I thought you saw that.
Oh, no, I didn't see it. Yeah. I think when you had done that part of your demonstration, the camera had dropped a bit.
Oh, okay.
And we didn't see the top row of the.
Yeah, okay.
Yeah. You didn't ask about this morning,
I'll make my temperature set point to 30. so that when it reaches 30, you can also check over temperature protection.
Alright. While we're at it though, could you bring up your block diagram? So I just have a few things here. The 120 volt AC to 18 volt DC adapter.
Yeah.
Okay. For me, that's not enough specifications for a AC to DC converter. There's missing at least another value. What value would you add to that?
The rating of that adapter is 1.1 ampere.
Okay, well, that definitely either that or the power rating. Okay, 1 and 2 needs to be there. Okay. The other thing is the humidity source.
Yeah.
Uh,
Should have one connection from microcontroller.
yeah, I know. For me, it was like, is that just something that he turns on manually or not? And then in your schematic, you started talking about it controlling, right? So that's definitely an error there.
Yeah, there's only a power input to it, no control input.
Yeah, so should be one input from the microcontroller to drive that.
Could you bring up your PCB? I'll tell you right away, color-wise, those are poor colors to pick. Okay, I know that that's the colors that are used inside whatever EDA you decide to use.
Yeah.
But when you're going to present them here, typically black on white is the way to go. Okay, it doesn't matter, you know, it's upper, lower, you can explain which one's which or whatever. While you were talking about this, you alluded to two things. You said, and I paraphrase, you did a polygon fill for better grounding. How does the polygon fill provide better grounding?
So it provides return path to the signal,
Pardon me?
proper return path to the signals. Yeah, I know it's not high speed, but it's.
No, but you don't need that to go to the. Your
And-
ground has to be grounded no
And this
matter
is
what.
also for heat dissipation, because if you can see, I have my regulators over here on the ground plates. So
Yeah, but that's
that-
what you said. You said poly for better. Actually, you have it right there. Copper polygons for better grounding. How does it provide better grounding? That's what I'm asking.
So I have used teaching wires. So it's 30 degrees, so over temperature. I close it now.
Answer the phone.
So yeah, so I was saying that I use teaching wires, so it kind of like reduces the loop inductance throughout the PCB.
Okay, so it's well,
So-
not inductance. So what's another word you want to look at besides inductance?
Thermal management and
No,
inductance,
that's
yeah.
something else. We talk about impedance.
Yeah.
So what do we want our ground to be? Do we want it to be high impedance or low impedance?
Low impedance.
So how do we make? How does this make it low impedance?
Because of wires. So for example, if sorry.
How does a ground plane? How is that lower impedance than a trace?
So this is my crystal over here. If I put wires over here with top and bottom ground planes, so loop inductance for the clock signals will be reduced.
Yeah. No, let's not talk about looping signals in a ground plane. What characteristic does it have compared to a trace that makes it lower impedance?
More area.
More, not area. Singular dimension, not area. What's instead of area, if we looked at a singular dimension between point A and point B, what characteristic is it? The distance that makes it better, or what's the other characteristic?
Height.
What am I-
Width.
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 It's wider. It's the widest trace you can have. Therefore, it drops the impedance significantly because of that. Okay. You also mentioned creepage. So talk to me about creepage. What is creepage?
Creepage is air gap between two signals, like two level of signals, like high level or low level. So that's air gap between those signals.
So
That's
what's
what
high
creepage is.
level and what's low level?
So this is 120 volt AC and this is DC. So both are on different.
Whoa. One's 120 volts AC.
Yeah.
DC is not a level.
Yeah, the
No,
different
no,
voltage.
DC is not a level. A level is a number. So what's the number on your DC side?
Like logic wise.
I don't know, voltage wise. You're the one that's talking about creepage, not me.
Yeah, so this is low level, this is high level.
Yes, so one's 120 volts. What's the other one?
That's 5 volts, 12 volt DC.
Okay, so we're comparing 120 volts to 12 volts. Okay, and you're using creepage to separate the two.
Yeah.
Okay, I think when they talk about creepage, they're talking about much larger
Yeah.
differences.
Yeah, I
When they
agree.
talk about high voltage, what's the definition of high voltage, Mr. Rose? I know that's your favorite. One of your favorite
From a
terms.
transmission perspective?
Sure.
Oh, what did we say in class? Do you remember? Could be 100,000 volts, you know?
Yeah, I don't think it's that though.
You know?
I think we, after over 600 volts typically is something we start talking about high voltages, okay? So, Bravo, you use creepage, I don't think you needed to use creepage here, okay?
Yeah, I agree.
Okay?
Yeah, this is just for precaution because
Well,
AC and DC.
you know, again, it comes back though to what efforts you're putting into this that are worthwhile versus what's just being way too cautious. There's a lot of PCB boards out there. We've seen a lot of PCB boards that use 120 volts mixed with lower DC, and they didn't take care of creepage, and everything's going to work out fine. Because 120 volts is not that significant for that. If you start talking about 400, 500, 600 volts, yeah, let's start talking
Maybe
about
I considered using creepage because I am using it with a relay. So maybe because of chattering of relay, it can produce an R code.
Again, no. The problem, the whole deal with that is the cost of that. That's extra cost when you go make a board, okay? That's a lot of extra cost, in fact. Routing inside of the board is very expensive. I'm sure you paid, if we looked at how much it costs you with and without, there's a significant expense, especially if you do a lot of boards, okay? So it becomes,
I was paying $0 for my PCB, so it was like there.
well, most companies don't pay $0,
Yeah, I get that.
okay? So that's the problem
Yeah.
there, okay? It's the same thing with your test points. I applaud you in putting test points. That's something we don't see very much of. But I think you definitely put too many test points. Bring up, you had one where you showed your terminal block there.
In schematic?
Yeah, one of the schematics had a terminal block with test points on it. Next one. Next one. No, keep going. That one.
Yeah.
Look at J7. That's a terminal block or connector.
Yeah, it's a terminal block.
It's a terminal block. Then you got TP17 and TP18. What's wrong with using J7 as your test points? And again, I'm talking about here, you know, today, in today's environment, we talk about design for manufacturing. So maybe this thing is only a one-of, and that's fine. But the reality is when you're going to walk out there, you're going to be designing because we want to put 1 million of these out or whatever. So 2 test points here like that, I don't know, 5 cents each at 1 million, it's a lot of money, right? So, and again, kudos for putting test points, but you don't have to put that many. You mentioned putting test points on pins you're not using. Why?
Because if I want to test my PCB and use extra ports for like.
You know what? There's
additional-
clips you can put on your MCU, and you can use them as test points. And you only have to put them where you want them, when you want them. And they're a lot cheaper than supplying a whole bunch. You know what I'm saying with that? So again, I applaud you for using test points. There's definitely points here where there should be test points, without a doubt. But there's definitely points where there should not be. TP7, TP18 for me is really useless. TP19, I don't know if that's useful. You can hear the relay click, can't you?
Yeah.
Why would you need a test point? You'll know if it activates or not. It'll click, right? If you go to where your in-circuit serial programmer is, you test point every part of that. I honestly don't know why you would ever want to do that. Test points on I2C is a good idea, but the test points on your J5 there, again, I don't know why you'd ever want to do that. All right, that's nobody. That either works or it doesn't. If it doesn't, you know, it's not the test points that are going to tell you if it works or not, right? Okay. So external switch controls, yeah, I can see that maybe having test points there. You know, that might or might not be, but I could also see myself just pulling the connector out and using, you know. So you know, again, you gotta think a little bit about how's this going to be deployed in that. Okay, but again, bravo, test points, yeah. Okay, just you have a lot of you have more test points there that I've seen VHF radios for aircraft have test points. Honestly, I mean, I've worked on a lot of VHF radios, and you have more test points in your little circuit there than I've seen a whole nav and communication radio have test points over it. Right? So, okay?
Yeah, okay.
Anybody else?
Well, you had a 120 volts to 18 volts DC wall adapter, right?
Yeah.
Why did you choose that over, let's say, a 120 volts to 12 volts DC? You weren't using 18 volts in your circuit, right?
Yeah, but I'm using 12 volt voltage regulator, so I cannot provide 12 volt input to 12 volt regulator.
Well, if you had a 12 volt adapter, you wouldn't need the regulator.
Is it a regulated adapter?
Yeah.
Then why wouldn't you bring 12 volts in, like he's saying, from a 12 volt regulator and eliminate that part from your circuit?
Yeah, I should have done that.
Yeah.
The efficiency would be
And cost, manufacturing cost, to
Yeah.
stay on one.
Also, yeah, I can do that.
I could see if you had any component that needed 18 volts to be powered, I could see that, but it wasn't used anywhere in the circuit.
Yeah.
Burning up electrons.
How do you set your limit, temperature limit? How do you choose the limit?
Like power temperature?
Like, yeah.
It was just for demonstration. You can set it like 40 degrees, 45 degrees. With this light bulb, it can go up to 40 degrees.
Okay.
So you can set it to 40 degrees input. This is just for demonstration, otherwise it would have taken like 20 minutes to reach there.
So the alarm goes off if it exceeds the set point that you've
Yeah,
programmed in?
yeah, you just saw it.
Maybe I can, one more, just let, your test,
Yeah.
the first block there says system effectively maintains the desired temperature range within the plus or minus 0.5% tolerance, showcasing its precision and efficiency in real-time control. But we have a little check mark here that says not sales pitch. That sentence there is 100% sales pitch. Okay, how does the tolerance, the accuracy, showcase precision and efficiency?
Accuracy.
Yeah, so precision, nothing there. And then there's second one, humidity control. It said the system accurately regulates the humidity level within the minimum deviation, maintaining a set humidity of plus or minus 2% accuracy, proving its reliability. I'd like to ask you, sir, what is the definition of the term reliability?
So it's like it's working which it is intended for.
That's not the term reliability. The term reliability means something that is consistent, efficient, or not efficient, but it reproduces itself over and over and over time, and it can be trusted to, that, having a 2% accuracy is not reliability, okay? So again, for me, this page here is a lot more of a sales pitch than it is test results, okay? Leave the marketing to the marketing guys and show us some data here, okay? And then show us what that data proves, okay? How you got to that 0.5% tolerance, how you got the 2% accuracy, and that's what I'm interested in. Afterwards, the marketing guys, they'll spin it this way so that the people that are gonna buy it are fooled by it or whatever, okay?
Yeah.
Just making sure, right?
Yep. Guess we're in time. Thank you. There he is.
No, man.
I was supposed to drink it.
You drink how?
I was supposed to drink it.
You think I'm drinking water?
I was supposed to drink it.
Well, by the way. There was very long. I get frustrated. But I think it's almost the same. Like when you put it in the order that's 700 I get really frustrated over that. I don't think it's
Yeah, maybe the round Está bien ahí.
Okay. Yeah, where's that Guillermo guy? Oh yeah, he's presenting. So he's here,
Sí, más o todo bien. Sí, lo que voy a hacer es tal vez mover después pero está bien, voy a poco y ya.
Y esa es la técnica de
when you look through it, you use the climate data, where is that?
The climate data is climate data is most often taken because it's taken between anywhere from 4 to 18 years on the cap. It's most common to get an accurate. But it doesn't really say for climate data.
Because he says the wind shear at 1 year, so as soon as the wind shears, that means probably the
It doesn't affect
yeah, so we have to see the hair.
Oh, you haven't? No? Oh, okay, well, you can do this one.
Yeah. But the unit has to be.
I
No, because I already finished this one, so this comes from now, that's why I'm asking. So it's like 80, not 10.
I had submitted the ones that I submitted the way I thought it was.
If you go to location, it tells you where it's measured. I told you it was in the song.
Gotta look for it.
Pretty easy.
Did you figure out my code?
Yep. I think I got it in the right spot there.
Well, next term, I don't
Absence? Okay.
I'll be working because
Yeah.
you can get some shells.
Yeah, probably are. You guys work with?
Not doing,
Oh, yeah. We need to talk about
because next year my like.
Yeah.
Are you gonna do ours?
Yeah, I guess we gotta get some people together and talk about how we want to do it. When you want to do that? Your answer for this week?
Okay, ordering some parts.
Shelving for the stock room. Get rid of those 1950s.
They're held by RJ.
No, it's not Ethernet cable. It's solid conductor. Yeah, it's probably $100 per wire.
Coaxial?
No, it's just grounding wire.
How much is it?
It's got a sheet on it. A white sheet. White. Yeah, it's probably.
Or DC.
Might be, yeah. I don't know.
Laps around the building.
You deal with stressful environment.
You know, dealing with wires on the structural side. World Trade Center.
It seemed like it was.
You may want to get together.
Sorry,
Tell them how to get there.
Oh my goodness, I have an appointment just to be there.
He does though, he knows.
What if I said that to you?
You said, you have an appointment?
Yeah, I'm just joking.
Oh.
Yeah.
You just
I got an appointment too. It's in Hotel Buchan. It's in Hotel Buchan. It's in Hotel Buchan.
Oh, you go to the fire.
Yeah. Yeah.
culture or something.
I've already done it.
The most relaxed one to be done.
Really? And Bruce? Yeah.
No, you were there.
Yeah, well, he was Bruce's.
So this volunteer just the fire department.
Yeah, we cleaned the hoses with that.
Hit your hoses so someone don't have to be. No, it's just we have some.
Oh, they just don't need one because they're.
No. I wish we had that.
That'd be cool. Yeah.
All right, so just before we continue here with the last presentation of the day, I just want to inform everybody here, the instructors and the students that at 3:15, 3:30, they're not to leave. There's a mandatory debriefing, and we're also going to feed you, so yeah. So it's mandatory because of that. I don't want to be stuck with all kinds of pizza, you know. And we will be taking a second attendance, okay, so stay for that, please. Having said that, so we're going to go through the last presentation of the day. All right, so Guillermo Pinedo, I finally got to get your name right there, is going to talk to us about his automated parking attendant. Take it away.
Thank you, Mr. Natal. So, good afternoon, everyone. Thanks for attending today, and welcome to the last presentation of the symposium session for this term. The name of my project is Automated Parking Attendant. My name is Guillermo Pinedo, and I'm just going to show you guys the process of developing my project. I'm part of the Electronics Technology Program in Industrial Controls Pathway. Moving forward to the agenda for today, we have the introduction, user functions, technical description, testing, and conclusion. For the introduction portion, I would like to say the reason that I picked this project is because I wanted to create something that I can apply and use it often. This device is created to control and limit the access of vehicles to a building. This device provides safety in the sense that filters the users, provides low price. It's a low price device in the sense or from the point of view that it operates or accomplish the task that it can be accomplished by a human. It's flexible in the sense that most of the parts of the device can be replaced with any further major connection or major modification. It's efficient since it's programmed, so the functions are timed. Either you provide an input and it's timed, so it wouldn't take longer than it's programmed. For the concept and design portion, I would like to start with my concept drawing. So starting on the front side, the first comment that I would like to talk is the sides of the enclosure. They're like angle cuts. That was designed expecting the tumbling due to the force of the boom barrier. So whenever goes up, I was expecting a movement of the enclosure. That's the reason I designed a wider bottom and a smaller top. On the front side, we have also two light indicators right here. So one of them is referring that it's full, the system is full, and the other one is referring that the system is available. For this device, the limit of vehicles is 5. It's a number programmable. I decided 5 just for demoing purposes. We have the keypad in the front, and this on the number 3 is a presence sensor to stop the movement of the boom barrier. Moving to the back side, we have the exit push button, and this another number 3 on the bottom of the enclosure is designed to enable the exit push button. So if the user if the sensor is not detecting, the exit function won't be enabled. On the left side, we have this small gate. It's designed for maintenance purposes. So if that wouldn't be there, you have to take apart the enclosure, and so it will be a major problem for that. Moving forward to the block diagram, starting for the keypad that we have on the left side. So I want to start with the number of power supplies that I have. I'm using 3 power supplies for this project. One of them powers the input section of the PLC. The other one powers the output section of the PLC, and a third internal power supply for the PLC the internal power supply powers the input, and another to power the motor. Sorry about the mistake. So starting with the keypad, the keypad is an independent device. What I mean for independent is because this device, the logic is independent for the PLC. So that means I program the users on the keypad, and then the device itself does the validation of the user and communicates with the PLC. So I can program the keypad without touching the logic on the PLC. In the lower part here, we have the 2 presence sensors. As I mentioned, one is located on the boom barrier to stop it, and the other one is to enable the exit push button. We have the exit push button, which concludes with the inputs for this project. We have the PLC receives the inputs. One of the steps that does is updates the counting variable, so it updates if it's full or not, or if it's within the parameters, and provides an output to enable either the full or available indicator. Depending on if the scans the sensors or reads the inputs of the sensors to provide to move forward for the open and close cycle. During that, depending of the state of this cycle, decides and evaluates what relays to activate. I'm using a DC gear motor for this project, so that means in order to reverse or to lower down the boom barrier, I need to reverse the direction of the motor. So that means that I have to switch the terminals. I'm going to explain about that further when I get to the wiring diagram. So the boom barrier is mechanically coupled to the shaft of the DC gear motor, and so that concludes the. Just another, I should mention that this is a condensed project. If I compare further in this presentation, I'm referring if we think about an actual installed in a building. So the elements of the project can be separated and installed in strategic positions to enhance the functionality of the project. I would like to start with the user function. There are three main functions. The first one is the keypad access. So the keypad access is located in the front. Once the user has to provide a 4-digit password. If the password is invalid or not registered, the keypad will just discard it, and the system won't activate or start with the open and close cycle. What I mean for the open and close cycle, I mean the user provides a password. Oh, sorry. The user provides a password. The boom barrier list. The systems provides a time to access to the vehicle to access a vehicle. Barrier drops and then goes to the original position, and then the cycle starts again. The time that I decide that I program for this project is 6 seconds, just for demoing purposes. The car might take longer than 6 seconds to pass through. This is how it looks. This is how the keypad how it looks like. It's a touch surface. They're not buttons. The keypad has a memory to save up to 2,000 users. And another feature for the keypad is that it can be combined using a access card. I didn't purchase any access card, but it's just one of the features. You can use either access cards or a password, 4-digit password. Moving forward to the function 2 is the exit push button. Same as another input, similar to the keypad input. The user presses the exit push button. If the sensor is sensing, it will enable the exit push button. So then it will start the open and close cycle. For the third function, this is one of the issues that I encountered. I had to develop this function because it was one of the issues when I was putting together the project. When I wanted to locate the barrier in the right position, I had no way to operate the boom barrier other than downloading a program and run the program. So it was not practical method to guess the timing or do testing or to locate the boom barrier in the right position. So that's the reason this function is more focused for an operator. What this function is just a switch or a push button to control the motor independently of the logic of the PLC. To operate this function in a safe way, the PLC has to be turned off to avoid a short circuit scenario. To start with the technical description, I would like to address the wiring diagram. So this is my wiring diagram. I would like to mention some of the notes that I wasn't able to show in this drawing, because the coding or the writing on the drawing won't be appreciated. So I have to zoom in the drawing to be able to be appreciated. One of the first note that I want to mention is the CD1 is not a fuse, it's a circuit breaker. So I use not the appropriate symbol for that. And PS1 and PS2, PS2 is connected to 2 amps circuit breaker, and PS1 is connected to a 6 amp circuit breaker. RL1, RL2, and RL3, they have an internal fuse, 6 amp fuse. The wiring in the motor, that is the lines that are a little bit wider, they're referring a AWG 16, and the rest of the wiring is 22. Okay, so to talk about the first element of my project, so the PLC is the PLC, which is the one that controls and coordinates the elements of the system. It has 2 sections, the input and the output section. The input section needs to be connected to a positive terminal of the power supply, and in order to read the input. I'm mentioning this because further I encountered another issue. When I was wiring the keypad, I noticed when I provided a valid password, the wiring provides a negative. When it was activated, the terminal that it was provided by the keypad, it was the negative one. So that means that the PLC won't read that negative. When it was closing the PLC reads the input when it closes the circuit. So when the keypad was activating, the PLC it wasn't able to read the input. So I had to modify my design, adding a relay to the system. What this relay does is just to switch the terminals of the power supply, meaning when the keypad is activated, then closes the coil of the relay and provides with a positive, connects the positive terminal to the PLC. So then the PLC can read it. The next element of my wiring diagram is the sensors. I mentioned what are those for, and what are they doing. So they're the 3 wires, and when the sensors senses, it connects, it triggers the internal switch and connects the terminal, the positive terminal to the PLC, and then it can read the input. Lastly, but not least, the motor. As I mentioned before, in order to do the switching for the terminals, I have to do an arrangement with 3 relays. So RL4, it only controls the position of the neutral. So that means the motor has the motor is a DC motor, so it has two terminals. However, if physically I have to connect four terminals to 4 cables to each of the terminal. So basically, RL4, what it does is controlling the position of the neutral, and RL2 enables the forward direction, and RL3 enables the reverse direction. With the help of the logic, it avoids any short circuit scenario. I'm going to show a little bit of my code for this presentation. The rest are just the light indicators, the push button, but that's for the wiring portion. This is I'm just going to show the 3 main functions of the coding. Is a ladder logic. The program is not a big program. It's about 12 kilobytes. So, and I'm just gonna show 3 of the main functions. So as we all know, the ladder logic or the PLC reads from top to bottom. That means the first value that I wanted to read is the neutral. So the PLC reads the state of the neutral to avoid going into short circuit position. Then there's the 2 input paths, and this is the time that I originally programmed to enable the motor to rotate in forward direction. For this third function, and it closes the open and close cycle, is the reverse direction. Same as the forward. For this motor, I enable for 0.6 seconds to rotate the motor. I have an issue with the motor. I had an issue with the motor, and I'm gonna explain forward on the conclusion section. For my testing section, so the first test that I run, it was a weight capacity test. I wanted to check if the motor won, or what's the limit of the weight capacity of the boom barrier before triggering the circuit breaker or blowing the fuses on the relays. So I connected the power supply. The motor is running with a 12 VDC, and it's connected to a circuit breaker to limit the current. I connected the ammeter to read the value of the current, the gear motor coupling system, and changing the weight of the boom barriers. This is the results that I got. So as a conclusion for this test, the maximum capacity that I would recommend to attach to the system is 1.5 kilograms, since the current is 5.17, which is really close to the 6 limit. I didn't want it to go to the very limit, since I didn't want it to risk the project at this point of the term. For my second test, I wanted to test the sensors and determine if the sensors were suitable for this project. The sensors are photoelectric sensors, which are composed for 2 elements, the ammeter and the receiver. The ammeter element throws a light beam, and then the object that the light beam that hits the light hits the object, reflects, and the ammeter receiver element detects the reflection or reads the reflection, and then triggers the switching to switch the connectivity to the PLC and read it. I tested several materials, because on these days we don't know what materials we can find in a vehicle, right? It can, depending of the position, it can be metal, rubber, or glass. In regards to the sensing area, it's not a conic sensing area. It's a sort of rectangle for 1 centimeter wide and 30 centimeters according to the data sheet of the sensors. This is the results that I found during my test too. Pretty much they're acceptable readings. I noticed, depending of the reflectivity of the surface, let's say if it was, for example, the wood that I tested, it was more than I expected, because it has like a sort of a reflected surface. So that's the reason I got this this measurement. And the metal that I tested, it was like a surface, like a not shiny surface. And just for since it's a light beam that it detects, I just did a test with a mirror, and obviously the sensing distance dramatically increases. Okay, moving forward to the conclusion section. So the system accomplished what is designed to do. Provides the efficient access and how is intended to do. The reason that I had to develop this project, it was achieved. I wanted to increase or extend my knowledge in programming, which this is my first experience programming in a technology such as Siemens. For the future improvements, the sensing capacity, I would like to increase the sensing area. However, it will depend of the building that is installed, whatever is suitable for the building. Another improvement that I would like to provide for this project is the sensor when controlling the barrier, because it's hard to limit the movement of the motor. So adding another sensor, the barrier will be controlled, and the boom barrier will be controlled in a more precise way. So you can, because right now the motor is too fast, so it's quite hard to control with the timers. So to avoid the timers control, I will do sensors. I just have one, as I explained before, and that's the best way to do, I'll say. What could I have done differently? I mentioned that I will talk about the motor speed. So when I was the original design for this project, it was the motor was running at 50 RPMs, and I found it was really hard to control it. So when I was testing it, the barrier was just passing the limits and turning sometimes almost all the circumference. The enclosure design, definitely I'm not a carpenter. I had a really hard time building the enclosure. It was quite challenging to accomplish it in 3 hours with Mr. Liger in the carpentry lab. Yeah, it was quite challenging, especially those angle cuts there. I planned to hold the maximum weight capacity, so the internal structure is 2x4. So dealing with those wide pieces of wood is not an easy task to do. And the last thing that I would do different is providing a interlock safety for the switching of the motor, mechanical and electrically. Yeah, that's another possible addition that I could have done differently. This is my references. And I would like to thank everyone that participated on this project. It was not myself, my family that is watching from back home. And this is it for my presentation purpose portion. So I would like to start with the enclosure. These handles that are on top of here, they're not part of the design. However, I had to install them because the transporting part, it was really hard to put it on the car and bring it here. And so the enclosure is like not light, right? Yeah. So that's the reason they're just temporary there, because it's supposed to be anchored to the ground, right? So, yeah, we have the two light indicators there, the keypad, and right now the counting is at 3. So, as I said, the limit is 5. So I'm gonna provide the password that I registered previously. That's 1235 and pound. So as I said, the counting was 3, so it's supposed to be 4 right now. As I mentioned, in regards to the, as you notice, when the boom barrier goes up, and as I explained, on the program portion is timed. It's timed whenever it goes up, and when it goes down, I have this sensor there to stop the movement of the boom barrier. So for the exit function. Right there. So, as I mentioned, to avoid invalid inputs and altering the counting on the system, if a car is not located there or on the sensing area, if anyone presses the exit button, nothing will happen. However, if a car is on the same. Yeah, sorry, it's
standing on its bumper.
Yeah. So it's it on the sensing area. The button enables. It's lighting up there, and system start up the opening and closing cycle again. And so the counting variable will count down. Another that I should mention, another feature is that for safety reasons, it will always count opens on the exit side, but whenever on the input side, on the entrance side, which is the keypad, it will just stop at 5. It won't go further than 5. And as I said, on the exit side will always provide the exit. However, the counting, it will go lower than 0. So that means it can control accurate the counting of 5. The last thing that so the switching controlling that It's right here. But I don't want it to do it because it's gonna decalibrate the boom barrier. So I'd rather not to do it because if I want to run it again, I have to like lift the enclosure because the boom barrier is long enough to hit the ground. So it's just for calibrating function. And that concludes to my demonstration section.
Do you pay people for finding bugs?
Sorry?
Do you pay people for finding bugs? Large companies that release programs sometimes, they'll pay their people, they'll pay their customers if they find bugs.
Oh, okay, like.
Do you do that? Because I think I found the bug.
Oh, really?
When you, first time when you hit the exit button without the car,
yeah.
I noticed the full went to available automatically. Your light went from full to available.
Oh, when I hit it without sensing?
Yeah, without the car sensing.
Oh, okay.
So you might want to,
yeah.
So you might just want to look at your.
Yeah.
You can send a check in the mail.
Yeah.
Oh, yeah. Yeah. Thanks.
Yeah.
We had minimal detail there.
Yeah.
Sorry about that.
No, it's not a big thing. Just I noticed when you hit it, it swapped the light over.
Oh, okay.
It didn't open like you said it would.
Okay.
And when you put the car, it opened, but it was already available, right?
Oh, I see. Yeah. Okay.
So, where do we want to go first? The wiring diagram?
Sure.
Yeah, it's kind of neat. Okay. You use the term neutral a lot here.
Neutral?
Yeah.
Mm-hmm.
Where's the neutral on this diagram?
Is the negative, I call neutral the negative terminal of the power supply. It's,
that's my point.
Yeah, what I was referring is to this terminal right here.
What's its
negative
property?
Yeah, what is the actual name of that line? Is it actually neutral?
Negative, or a column?
Yeah, where's the neutral on this diagram?
Here.
Right, what's the difference between that line and the other one?
I'll say this one is a AC system.
Yeah, it's
and
AC.
This one is a DC system.
Right. And what place does the term neutral have in a DC system?
What place?
Yes.
Sorry?
Yeah, what place does the term neutral have in a DC system? Does it have a place there? Is that an accepted term that we use with DC?
No, it's not accepted.
Okay, good.
Yeah.
I was going to say, 'cause
No, yeah,
up until today, it never had been for me. So.
Yeah, sorry, I misused the negative terminal. Sorry about that. Yeah.
Okay, no problem. Let's see. Anybody else have anything about the wiring diagram? We got other questions, but not about the wiring diagram. No? Okay. You talked about the weight capacity of the motor to handle the boom.
Correct.
And you were saying 1.5 kilograms.
That's correct.
Okay. What could be done to improve the weight handling capacity of the motor? So I want to increase the weight of the boom without actually increasing the size of the motor.
Reducing the speed?
Perhaps. What if I wanted it to perform the same or even better?
So I don't want to change the speed.
Yeah, maybe.
I want to keep the same, or maybe even improve the speed with a much longer, heavier boom.
Yeah.
What could I do to?
Sorry.
What could I change about this boom? Okay. Or what could I add to it without changing the motor that would improve the motor's ability to operate this heavier boom?
So I just want to ask if we're talking about an electrically solution or a mechanically solution.
Well, maybe it would be a mechanical solution.
Okay. So if I'm just gonna go to the testing diagram. So if
physical / mechanical. Perhaps.
Yeah. So if I decided to go for a mechanical, I could have maybe a gear system or a pulley system to, like you said, either get a higher torque or.
You could do that.
Yeah.
However, that would add, I think, unnecessary complexity and perhaps increase the need for servicing, because then you've got a lot of extra mechanic gears and pulleys and what have you. I was thinking of a more of a simpler solution. What could you add to the boom to make it easier for the motor to lift it?
Okay, so if we discard the gear solution, the gears, yeah, a system like a counter weight on the other side.
Like a counterweight, right?
Yeah, yeah.
Yeah. So you, what's that? Or a spring, right?
Yeah.
Something to counter the, there's a lot, like you say, a lot of mass out on one end, right? So if you put something to balance that out on the other end, a spring, a counterweight, yeah, you could, I think, get a lot more performance out of the motor, and it would actually, I think, extend the life of the motor too, because you wouldn't require that it draws so much current to lift that heavy boom. Right? So that's something you could consider.
Yeah, yeah.
You talked about, while we're on the boom, you talked about calibration of the boom. I find that interesting, and can you elaborate on that? Like, when you say calibration, what are you calibrating about the boom exactly?
The position of the boom barrier. The position of the boom barrier.
Which position? Because I saw it in lots of positions, right?
Oh, the standby position, like,
okay.
Like what it is right now.
So the stop, or the standby, or the down position, I guess. Yeah.
Yeah.
Why not have like physical stops?
Yeah, I was kind of wondering that.
Physical stops?
Yeah. Why wouldn't you have just like, you could have actually, while you were in the carpentry shop, fabricated a physical stop.
Yeah.
Right mounted to the side of the unit where it just comes down and stops, right? Why did you choose the way in which you did that as opposed to using a physical method of stopping?
Yeah.
Those are kind of questions that I was wondering.
Yeah, so I didn't go for that kind of system because I thought two possible causes. One of them will be damaging the coupling of the boom barrier, since it's gonna like stop and provide mechanically vibration on the screws and on the other part of the screws. Whatever, I don't remember.
Like bolts and nuts?
Yeah, the nuts that you tied it up.
Yeah.
So it's going to cause damage on the mechanically coupling of the boom barrier. That's one. And the other one, I thought you're kind of stopping or drastically the motion, the movement of the shaft. So I thought it might cause damage to the motor. It was just estimations. I didn't know if, just possible estimations.
Okay.
I didn't try it.
That's fair. Now talk to me more about the calibration. What are you actually calibrating are you calibrating for a certain position? Is it like a horizontal position that you're calibrating for?
Correct, since the lifting portion of the cycle, it's time. So then I'm calibrated on the sense that that timing is going to be long enough, long time enough to reach the higher position and goes and lower it down. So calibrated in the position that it's supposed to be due to the timing of the program
And
or
how,
the logic.
and how does the motor know what position it's in?
The motor,
Yeah.
the motor doesn't know.
So what part of your project tells the motor where to stop?
And you mean on the upper, on the lifting position, or on the
When it gets back down? Well, I mean, we talk about both, but let's talk about the horizontal position. How does it know where to stop?
When lowering down?
Yeah.
When lowering down is the sensor.
So the one we're seeing in front of us right here?
Correct.
Okay.
And the other one is two ways to stop it. One is timing, and the other one is the sensor. The timing is kind of a safety measure,
right?
Because the sensor is able to stop it. And I mean, if by any circumstances doesn't sense it and stop it, and it's not timed, it's gonna go right through the ground and destroy the boom barrier, right?
So I'm trying to figure out what needs calibration, because your sensor position isn't changing. And so as that boom comes down, why isn't it stopping immediately after it clears it, or either clears the sensor, or I don't know what your logic is there, but why isn't it stopping exactly horizontal?
Because the timing on the triggering of the sensor is not fast enough compared to the speed of the motor. So if like this as an improvement that I mentioned, is run a slower movement of the boom barrier, either by implementing one of the mechanisms that you mentioned, or the solution that I proposed, it was lowering the speed of the motor. So the sensor, the trigger of the sensor is not fast enough as the motor. Yeah. So
Another thing you could consider is like a feedback system. What are you talking about? That you did PNID or something like that, where as you're getting closer, you can slow it down, right? Because I notice that sometimes you have an overrun. Right? So what's happening is you're killing the motor, but the momentum keeps it going, right? So you could have some kind of feedback mechanism to know where you're at and where you're going and when to stop, right?
Oh, okay.
How to slow it down and stop. And then
like to reduce, like to electrically reduce the motor. That's what.
Well, as you're getting closer to where you want to stop, you're going to start slowing it down. So what happens then is when it finally gets to where it's at, it's not going very fast, so it stops there, right? What you're doing is you're coming down. Once you kick that sensor, you stop it, right? But then the momentum just keeps pushing it down, so it'll overshoot it. You know, like an example, if we were outside with this and the wind or a crow landed and it moved what's going to happen now is the next time it opens, it will not necessarily open all the way, right?
Okay.
Okay. But with a feedback mechanism for example, in PNID, you could tell that you're not there. You're not in the right place. So when it goes up, it'll stop where it's supposed to, and when it comes down, it'll come back to where it's supposed to, right? But that's more than one sensor at that point, right?
Oh, I see.
Track where you're at.
Okay. The sensor we're looking at here, how does it work? It's sending, it's photoelectric, you said, so it's sending a light beam out. What's reflecting it back? Is there a reflector on the reverse side of that boom that I can't see?
No, not really. It's just the bare wood.
Bare wood?
Yeah, the bare wood, because this is made of wood, right? So the bare wood reflects. And, and that was my second test about to test the different reaction or the sensing capacity of different materials that possibly encountered by the sensors. Yeah, and 30 centimeters for that sensor might not be like the best as the data.
So what photoelectric mode is that that's being used here?
What photoelectric mode?
Yeah.
Photoelectric mode.
There are 4 of them. Which one is this one using?
Reflection?
That's not one of the 4.
That's another one.
No. Anyway, you should look that up.
Okay.
I guess we're in time, aren't we?
Yeah.
Yeah, okay.
Thanks everyone.
It's done?
It's done, finally.
Yeah.